The year 1958 is recognized as a structural turning point in modern industrial development because it introduced the integrated circuit, a device that consolidated multiple electronic components on a single semiconductor substrate, allowing the electronic systems of the mid-20th century to move beyond the limitations of discrete components. Before this point, electronic equipment relied on vacuum tubes or single transistors wired together in complex assemblies. These systems consumed significant power, generated substantial heat, and required continual maintenance. The demands of scientific computing, aerospace guidance, telecommunications, and industrial automation were increasing, yet no practical method existed to produce compact, reliable, high-complexity circuits at scale. The emergence of the integrated circuit provided the needed solution and opened the technological path that defined industrial transformation for the next several decades. In September 1958, Jack Kilby at Texas Instruments constructed the first functioning integrated circuit. Kilby's prototype was built on a germanium substrate and combined essential circuit elements, a transistor, a capacitor, and a resistor, on a single semiconductor piece. Because monolithic interconnects had not yet been invented, Kilby used fine gold wire to connect the components. Although the prototype was not suited for mass production, it demonstrated beyond theoretical argument that a complete circuit could be fabricated as one solid structure rather than assembled from numerous discrete parts. This demonstration altered the trajectory of electronic engineering and showed that complexity could grow without requiring proportional increases in physical size. A second key development came from Gene Horney of Fairchild Semiconductor in 1959, when he devised the planar transistor process. Horney's method introduced a stable oxide layer and photolithographic patterning on a flat silicon surface, creating a structure that improved reliability and allowed consistent reproduction. Building directly on Horney's innovation, Robert Noyce at Fairchild proposed and developed the planar integrated circuit between 1959 and 1960. Noyce's approach embedded metallic interconnections onto the surface of the silicon wafer, enabling the manufacture of multiple identical circuits across the wafer simultaneously. He filed his patent application in 1959, and it was issued in 1961. The combination of Kilby's working principle, Horney's planar transistor, and Noyce's planar integrated circuit established the technological foundation for repeatable, scalable semiconductor manufacturing and defined the practical architecture of integrated circuits for decades. The transition from germanium to silicon was essential for industrial viability. Silicon possessed a superior native oxide, stronger thermal stability, and fabrication characteristics compatible with large-scale production. Advances in silicon purification, diffusion furnaces, and photolithographic resolution during the late 1950s and early 1960s allowed consistent manufacturing of semiconductor devices. Early integrated circuits contained only a few components, typically between 5 and 10, but their reliability and performance surpassed discrete assemblies. As fabrication yields improved, the cost per function began declining rapidly. This cost reduction made it possible for industries beyond defense and aerospace to consider integrated circuits as practical alternatives to traditional assemblies. The emergence of the integrated circuit reshaped the organizational and geographic structure of the semiconductor industry. Fairchild Semiconductor became a principal institution, developing new lithographic techniques, oxidation processes, and diffusion controls that supported higher yields and more complex designs. Many Fairchild engineers later founded new companies, including Intel in 1968, contributing to the formation of an innovation ecosystem that shaped future microelectronics development. Texas Instruments advanced commercial production techniques and demonstrated early applications in defense and industrial systems. Universities expanded coursework in solid-state physics, electrical engineering, and microelectronics to meet increasing demand for highly specialized labor. By the early 1960s, these developments signaled the establishment of a new industrial discipline with long-term research requirements and rapid advancement cycles. The significance of the integrated circuit becomes clearer in comparison with computing technology before its introduction. Early computing machines, such as ENIAC, operational in 1945, and UNIVAC-I, delivered in 1951, relied on vacuum tubes and needed entire rooms to house their assemblies. Transistor-based computers of the mid-1950s improved performance and reliability, but required extensive manual wiring and assembly. Integrated circuits offered a method to increase logic density without increasing size or heat output. Although they did not immediately enter general commercial computing, integrated circuits appeared in specialized systems in the mid-1960s for aerospace, guidance, and defense applications. Their smaller size, improved reliability, and reduced power requirements made them suitable for avionics and other mission-critical equipment. Broader commercial adoption expanded as device costs decreased through the late 1960s and early 1970s. Government procurement accelerated this process. The United States Department of Defense and NASA became major early institutional purchasers of integrated circuits. Programs involving missile guidance, satellite communications, and spaceflight instrumentation required compact, high-performance electronics, providing stable, high-volume contracts that supported industrial scaling. These purchases raised manufacturing quality standards, increased yields, and reduced defect rates. The effect of this early demand was not limited to military systems. It helped integrated circuits reach levels of affordability and reliability necessary for general industrial and commercial implementation. Telecommunications firms began evaluating integrated circuits during this same period. Electromechanical switching systems had dominated telephone networks for decades, but they limited throughput and required regular maintenance. Integrated circuits offered a path toward fully electronic switching equipment capable of higher speeds and greater reliability. Scientific and industrial instruments also benefited from integrated circuits, gaining faster signal processing and improved measurement precision. Industrial control systems adopted integrated circuits to support more complex monitoring and regulation tasks. Across these fields, the pattern was consistent. Integrated circuits enabled reductions in size and power consumption while increasing functionality. International developments reinforced this trajectory. Japan, guided by industrial policy coordinated through the Ministry of International Trade and Industry, invested heavily in microelectronics during the early and mid-1960s. Japanese firms expanded fabrication capacity, refined materials processing, and built a workforce capable of sustaining long-term semiconductor production. Western Europe contributed through firms such as Philips, Siemens, Mullard, and Thomson CSF, which produced competitive devices and participated in early collaborative research efforts. The Soviet Union pursued semiconductor development but encountered institutional and resource constraints that slowed progress relative to the United States and Japan. These global dynamics indicated that semiconductor technology would become a central factor in long-term industrial competitiveness. Understanding why the integrated circuit is considered the opening point of the third industrial revolution requires examining its capacity for scaling. In 1965, Gordon Moore published an observation in Electronics magazine noting that the number of components in commercially practical integrated circuits had been doubling approximately every year. This trend, later known as Moore's Law, described an empirical pattern rather than a physical law. By the early 1970s, the doubling interval was commonly expressed as roughly 2 years due to changes in fabrication capabilities and economic trade-offs. Despite fluctuations, the long-term exponential trend remained consistent for decades. Each increase in component density reduced cost per function and expanded performance. As soon as new levels of complexity became affordable, industries adopted them, reinforcing the scaling cycle. By the mid-1960s, integrated circuits were entering specialized computing environments, telecommunications systems, scientific instruments, and industrial control equipment. Semiconductor fabrication facilities were expanding, and research institutions were investing in improved lithography, materials purity, and circuit design methods. These developments created expectations for future technologies that would exceed anything from earlier decades. The material and industrial foundations necessary for microprocessors, digital telecommunications, programmable automation, and large-scale information systems were already in place. Integrated circuits made it possible to increase complexity without increasing physical dimensions, and this capability defined the technological possibilities of the following decades. The developments between 1958 and 1961 marked the beginning of the Third Industrial Revolution. They introduced a device capable of supporting new forms of computation, communication, and industrial control. Integrated circuits allowed electronic systems to become more compact and more powerful, enabling structural changes in production and administration across multiple sectors. Without the integrated circuit, the advances that followed would not have occurred at the speed or scale observed from the late 20th century onward. The period from the late 1950s through the early 1960s forms the foundational layer of the broader technological transformation initiated by the integrated circuit. While the invention of the integrated circuit created the physical basis for scalable digital systems, the accompanying developments in computing architectures, electronic components, telecommunications infrastructure, and institutional research structures established the environment in which digital systems could operate and expand. The transition from vacuum tube computing to transistor-based architectures was already underway by the mid-1950s, but its full impact became visible in the late 1950s. Transistors reduced power consumption, lowered heat output, and increased component lifespan compared to vacuum tubes. Machines such as the IBM 704, introduced in 1954, demonstrated the advantages of transistorized logic and floating-point computation for scientific and engineering tasks. The 704 operated with approximately 4,000 vacuum tubes, consumed around 100 kilowatts of power, and required specialized cooling infrastructure. Its successor, the IBM 7090, introduced in 1959, implemented transistor circuitry and delivered roughly 6 times the processing speed of its predecessor, depending on workload type, while reducing power consumption and improving reliability. These early transistorized systems illustrated the performance advantages of solid-state designs, even before integrated circuits became widely available. During these years, computing remained a domain of government agencies, research laboratories, and large corporations capable of supporting the costs of installation, maintenance, and staffing. Computing centers required controlled environments, skilled operators, and programming personnel familiar with assembly languages or early high-level languages. Despite these limitations, the demand for computational capacity grew rapidly. Scientific research projects, military programs, and industrial logistics increasingly relied on automated data processing. As a result, institutional investment in computing infrastructure expanded steadily. The number of installed computers worldwide rose from a few thousand in the late 1950s to more than 7,000 by the early 1960s. Using United States and Western European installation data as the basis for global estimates reflecting both increased demand and improved production capabilities. Telecommunications infrastructure expanded in parallel with computing development. Microwave relay networks, coaxial cable lines, and early satellite research programs created the capacity for long-distance, high-throughput communication. By the end of the 1950s, microwave transmission lines formed the backbone of national communication systems in the United States, Western Europe, and Japan. These networks offered higher bandwidth than traditional telephone lines and could support data transmission at rates necessary for emerging digital applications. Microwave towers spaced approximately 30 to 40 kilometers apart provided reliable line-of-sight transmission, enabling multi-state or multi-region communication links. The integration of digital techniques into these networks was still limited, but the infrastructure was in place for future upgrades. Cold War research exerted a substantial influence on the direction of technological development during this period. Defense agencies in the United States and Western Europe invested in computing, radar, cryptography, missile guidance, and early command and control systems that required improved electronic capabilities. Programs such as the Semi-Automatic Ground Environment, which began operation in 1958, depended on large-scale computing and real-time data processing. SAGE used multiple and /FSQ, 7 computers, each containing tens of thousands of vacuum tubes and numerous transistors, to coordinate air defense radar data across multiple regions. Although SAGE predates widespread integrated circuit adoption, its scale and computational demands illustrated the need for more compact and efficient electronic systems. The system's operation required thousands of personnel and consumed millions of watts of power, demonstrating the limitations of pre-IC architectures and underscoring the importance of technological miniaturization. Programming practices evolved rapidly during this period. High-level languages such as Fortran, introduced by IBM in 1957, and COBOL, standardized in 1959 through industry, government committees, expanded the accessibility of computing. Fortran's optimization for scientific and mathematical work made it suitable for engineering, physics, and early numerical simulation tasks. COBOL standardized business data processing logic, allowing corporations and government agencies to write and maintain administrative software more efficiently. The adoption of these languages reduced dependence on machine-specific assembly code and allowed software to grow in size, complexity, and portability. This development helped create the conditions for software engineering to emerge as a recognized discipline. The establishment of time-sharing systems in the early 1960s represented a significant change in how computing resources were used. Traditional batch processing required users to submit programs and wait for processing cycles to complete. Time-sharing systems allowed multiple users to access a computer interactively through terminals, allocating small slices of processing time to each user. Projects such as MIT's compatible time-sharing system, first demonstrated in 1961, showed that computational resources could be shared efficiently among numerous users. CTSS allowed dozens of terminals to operate concurrently, reducing idle time and improving productivity. Time-sharing marked a step toward the networked computing environment that would emerge in later decades and demonstrated that digital systems could support real-time interaction. Institutional developments complemented these technical changes. Government laboratories, university research centers, and corporate research divisions expanded their focus on solid-state physics, digital communication, and systems engineering. Funding programs from national science agencies supported advances in integrated circuit fabrication, transistor design, and materials science. Research partnerships between universities and industry strengthened talent pipelines and accelerated the transfer of laboratory results into commercial products. In the United States, organizations such as Bell Laboratories, IBM Research, and government-funded defense laboratories formed the core of early digital research. In Western Europe, firms including Siemens and Philips collaborated with national laboratories on semiconductor and telecommunications technology. In Japan, companies such as NEC, Toshiba, and Hitachi pursued transistor and early integrated circuit research supported by coordinated industrial policy. Telecommunications switching technology progressed during this period toward electronic systems capable of supporting digital communication. Electromechanical relay-based switches limited the speed and complexity of telephone networks. Beginning in the late 1950s, research teams in the United States and Europe developed electronic switching systems that used transistors to route calls more rapidly and reliably than mechanical relays. Although commercial deployment of fully electronic switches would not become widespread until later in the 1960s and 1970s, the foundational work during this period established the architectures that future networks would use. Electronic switching laid the groundwork for data communication protocols and higher capacity networks that became essential in later decades. Advances in instrumentation and industrial control reflected similar trends. Digital measurement equipment, oscilloscopes with transistorized circuits, and automated test instruments improved the precision and speed of scientific research. Industrial facilities adopted early electronic controllers that regulated temperature, pressure, and chemical processes with greater accuracy. These systems frequently used transistors and early hybrid circuits, demonstrating the value of solid-state electronics in both laboratory and industrial settings. The increasing complexity of these control systems foreshadowed the programmable logic controllers and distributed control networks that would become common in later phases of industrial automation. The global diffusion of these technologies progressed unevenly but steadily. The United States and the United Kingdom maintained large computing installations for research, defense, and administrative tasks. Western European firms expanded transistor production and invested in early integrated circuit research. Japan strengthened its industrial base through targeted investment in electronics, emphasizing manufacturing quality, materials processing, and workforce training. The Soviet Union invested heavily in computing and radar research, but faced barriers in semiconductor fabrication and mass production. Despite these disparities, the global trajectory moved consistently toward digital systems and solid-state electronics. By the early 1960s, the number of computers worldwide had increased significantly, and the distribution of computing systems reflected industrial capacity and research investment patterns. Telecommunications networks grew in bandwidth and reliability, creating an infrastructure increasingly suited for digital traffic. Research institutions refined semiconductor materials, developed early integrated circuits, and created production techniques that improve consistency and yield rates. High-level programming languages and time-sharing systems expanded access to computing resources, and early automation systems demonstrated the advantages of digital control. These developments created the environment necessary for the integrated circuit to transition from a laboratory innovation into the foundational component of industrial society. The digital foundations formed in the late 1950s and early 1960s provided the computational, communication, and institutional scaffolding that supported subsequent breakthroughs. Without these developments, transistorized computers, microwave communication networks, standardized programming languages, time-sharing systems, early electronic switching, refined semiconductor fabrication, and sustained research investment, the later emergence of microprocessors, digital networks, and large-scale automation would not have been feasible. The early digital era established clear expectations for future systems: increased reliability, reduced size, greater processing capacity, and improved communication speed. These expectations, mapped onto the capabilities introduced by the integrated circuit, prepared the way for the rapid industrial transformation that unfolded from the mid-1960s onward. The technological structures established during this period formed the stable base upon which the Third Industrial Revolution advanced. The early 1960s mark a distinct phase in the modernization of industrial production as numerical control, transistorized control systems, and the first industrial robots entered manufacturing environments. These developments occurred during the same period in which computing, telecommunications, and semiconductor technology were establishing the foundations of the digital era. While integrated circuits were still in early development and not yet widespread in commercial equipment, the principles of automation advanced rapidly. Factories in the United States, Western Europe, and Japan introduced electronically controlled machining systems, automated handling devices, and continuous process control technology. These efforts altered production methods, improved consistency, and increased output across several industries. The years from 1960 to 1964 represent the transition between traditional mechanized production and the early stages of digitally influenced automation. Numerical control, originally developed in the 1940s and 1950s through United States Air Force and MIT collaborations for precision machining of aircraft components, began spreading into industrial use during this period. Numerical control systems directed machine tools through coded instructions recorded on punched tape. These instructions controlled movement across multiple axes with precision exceeding the capabilities of manual operation. During the early 1960s, manufacturers in aerospace, automotive, and heavy machinery industries increasingly adopted numerical control to produce consistent, complex components with tolerances measured in thousandths of an inch. Although early systems remained costly and required specialized programming skills, They offered advantages in repeatability, accuracy, and throughput that manual machining could not match. The introduction of numerical control influenced factory organization significantly. Highly skilled machinists continued to play essential roles, but workflows shifted toward programming, monitoring, and maintaining automated systems. Production lines grew more dependent on engineering design files, automated routines, and standardized component geometries. Machine tool builders such as Cincinnati Millicron, Giddings and Lewis, and Kearney and Trecker expanded their offerings to include machines compatible with numerical control. These machines incorporated transistorized circuitry and solid-state logic components that allowed more stable and reliable operation than earlier electromechanical control systems. Although integrated circuits were not yet widely used in industrial equipment, the transition to solid-state control marked a decisive break from relay-based automation. In 1961, General Motors installed the Unimate robot at its Turnstep plant in New Jersey, marking the first operational industrial robot deployed in a factory. Developed by Unimation, a company founded by George Devil and Joseph Engelberger, Unimate used hydraulic actuators and a programmed sequence of movements stored in a magnetic drum memory. Its initial task involved handling and stacking heated die-cast metal components, a process that required consistency and involved temperatures unsafe for manual handling. The introduction of Unimate demonstrated that robot systems could perform repetitive, hazardous, or high-precision tasks with reliable consistency. Although early industrial robots were limited in capabilities, expensive to install, and required specialized maintenance, they represented a major conceptual step toward automated production lines. The emergence of industrial robotics in the early 1960s reflected broader institutional developments. In the United States, the aerospace and defense industries had pushed for automation technologies to improve production quality and reduce variation in complex assemblies. In Japan, industrial policy organizations monitored developments closely, recognizing the potential long-term significance of robotics and numerical control for national competitiveness. Japanese firms such as Kawasaki licensed robotic technology from Unimation during the late 1960s, but interest and preliminary planning began earlier. Western European firms explored automation in the automotive and machinery sectors, often encouraged by government-sponsored modernization programs. Although adoption patterns varied, the direction across all industrialized regions was toward greater mechanization and electronic control. Automation extended beyond manufacturing machinery into industrial process control. Chemical plants, petroleum refineries, and power stations adopted electronic controllers capable of regulating temperature, pressure, and flow rates with greater stability than manual or mechanical systems. These early controllers often used transistorized circuits and analog computing modules. Distributed control was not yet feasible, but centralized electronic panels offered operators the ability to monitor multiple variables simultaneously and respond more rapidly to deviations. In the early 1960s, industries with continuous production processes, such as petrochemicals, steelmaking, and pulp manufacturing, used such systems to increase yield consistency and reduce waste. The benefits of automatic regulation became increasingly measurable, reinforcing investments in automation. Automation also influenced quality assurance practices. Manufacturers introduced electronic measurement systems capable of inspecting components with precision beyond manual instruments. Coordinate measuring machines, early forms of which appeared during this period, allowed accurate dimensional analysis of machine parts. Automated inspection improved process feedback, enabling factories to identify deviations earlier and adjust production settings. These developments contributed directly to improved product reliability in industries such as aerospace, electronics, and automotive manufacturing. Labor patterns began showing gradual but noticeable shifts. Automation did not eliminate factory jobs during this period, but it changed the skills required. Operators needed training in programming, system monitoring, and machine maintenance. Technical training programs expanded, and companies increasingly required employees to understand automated systems' logic and mechanical structure. Unions in several countries monitored automation trends closely, negotiating training provisions and safety protections. Although major displacements did not occur in the early 1960s, the introduction of robotics and numerical control signaled long-term changes in industrial labor structures. Government agencies and industrial research institutions tracked automation developments through reports, pilot projects, and technology assessments. In the United States, the National Science Foundation and the Department of Defense funded research on automated manufacturing systems, materials handling, and control devices. Western European governments supported modernization programs aimed at increasing industrial productivity, including the adoption of automated systems. Japan's Ministry of International Trade and Industry monitored automation trends systematically, preparing strategic guidance that would influence Japanese robotics development in the 1970s. These institutional actions demonstrated recognition of automation's significance in long-term industrial planning. Automation also affected production economics. Numerical control systems reduced scrap rates, shortened production cycles, and allowed more flexible part designs. Although upfront investment costs remained high, long-term savings in precision industries justified adoption. Factories that implemented automated systems reported measurable improvements in consistency, enabling new levels of standardization in assembly line manufacturing. The establishment of tighter tolerances allowed more reliable interchangeability of parts, an essential condition for modern mass production. Automation contributed to these improvements by enabling manufacturing processes that were less dependent on manual variation. In addition to machining and assembly, automation influenced materials handling and logistics inside factories. Early automated guided vehicles and conveyor systems moved components between workstations. These systems reduced manual handling errors, improved safety, and supported continuous workflow. Storage and retrieval systems using electronic controls enabled better management of inventory and work-in-progress materials. These developments contributed to layout changes in factories, emphasizing flow optimization and reducing downtime. The adoption of automation created a demand for more advanced computing interfaces. Although early automation systems often used analog electronics or simple digital logic, researchers and engineers recognized the potential advantages of combining automation with computer control. Pilot projects explored computer-directed machine tools, real-time monitoring of production variables, and automated scheduling. Although limited in capability, these experiments introduced concepts that later became central to computer-integrated manufacturing. Automation developments during this period occurred alongside broader changes in global industry. The United States remained the leader in automation technology, driven by aerospace, defense, and automotive sectors. Western Europe adopted automation selectively, influenced by industrial structure and national modernization policies. Japan demonstrated growing interest in automated systems and was prepared to expand significantly in later decades. The Soviet Union explored automation for heavy industry, but relied heavily on mechanical systems due to challenges in semiconductor fabrication and digital control. By 1964, automation technologies had progressed sufficiently to demonstrate a clear shift in industrial organization. Numerical control systems were widely recognized as essential for precision manufacturing. Industrial robots, although still rare, have proven their value in repetitive and hazardous tasks. Process industries had integrated electronic controllers that improved consistency and reduced variability. Quality assurance methods increasingly depend on electronic measurement systems. The cumulative effect of these changes marked the transition from traditional mechanized production to electronically guided industrial systems. These developments established the immediate context for subsequent technological changes. Automation in the early 1960s demonstrated the feasibility of electronically controlled manufacturing, created new expectations for reliability and precision, and expanded the role of engineering logic in production processes. As integrated circuits matured and became more widely available in the mid to late 1960s, they would merge with these automation practices to create more powerful, flexible, and compact control systems. The groundwork laid in this period defined the architecture of future industrial robotics, computer-integrated manufacturing, and digital automation. The years from 1960 to 1964, therefore, represent a critical early stage in the third industrial revolution. Automation entered factories in measurable and permanent ways, supported by numerical control, transistorized controllers, and the world's first industrial robots. These developments, combined with advances in computing and telecommunications from the previous decade, created a new industrial environment in which digital control would gradually replace manual and mechanical methods. The trajectory of industrial modernization that followed was shaped directly by the innovations introduced in this period. From 1963 to 1968 represents a major escalation in computing capability, system architecture standardization, and institutional dependence on digital technology. During these years, mainframe computing reached new levels of performance, reliability, and commercial adoption. The introduction of unified computer families, advances in programming languages, expansion of time-sharing, and early progress in software engineering reshaped how governments, corporations, and research institutions operated. These developments took place while integrated circuits were beginning to mature and while automation in industry was accelerating, creating a technological environment that supported the emergence of increasingly complex digital systems. The years from 1963 to 1968 formed the transition from specialized computing environments to large-scale, multipurpose computing infrastructures. The most influential development of this period was IBM's System/360, announced in April 1964. System/360 introduced a unified architecture across multiple models, allowing software compatibility and program portability between machines of different performance levels. This represented a significant departure from earlier industry practice, where each computer model often required unique software and programming methods. IBM offered the 360 in several configurations, ranging from smaller systems with limited memory to large mainframes capable of substantial scientific and commercial workloads. This uniform instruction set architecture allowed organizations to scale their computing capacity without rewriting applications, significantly reducing long-term software costs. System/360 quickly became an industrial standard, influencing global computing patterns for decades. System/360 also introduced hardware innovations that increased performance and reliability. Although early models still used transistor-based circuits rather than fully integrated circuits, IBM employed advanced solid-state logic modules with improved switching speeds. Memory capacities increased, with high-end models supporting hundreds of kilobytes to several megabytes of magnetic core memory. Input-output operations were streamlined through standardized channels, allowing faster data movement between storage, terminals, and processing units. Peripheral devices such as disk drives, tape systems, and printers became more capable and more tightly integrated with system architecture. The introduction of 2,311 disk drives and subsequent storage units expanded capacity and improved access times compared to earlier drum storage systems. The success of System/360 significantly altered the computing industry. Competitors in the United States and abroad faced pressure to adopt compatible or comparable architectures. Companies such as Honeywell, Burroughs, Univac, and NCR introduced systems that competed in specific sectors but struggled to match IBM's architectural unification. In Western Europe, firms such as Siemens and ICL pursued developments in compatible mainframes, while Japanese firms expanded their computing capabilities through licensing, domestic research, and government-supported programs. System/360's broad adoption reinforced IBM's position as the dominant global supplier of mainframe computing during this period. While System/360 defined commercial and administrative computing, advances in scientific computing also accelerated. Machines such as the Control Data Corporation CDC 6600, introduced in 1964 and often cited as the first widely recognized supercomputer, achieved processing speeds significantly beyond those of contemporary mainframes. The CDC 6600 employed a reduced instruction set, parallel functional units, and high-performance peripheral processors to manage I/O operations. This architecture allowed the system to reach speeds of around 3 million instructions per second, enabling complex simulations and scientific calculations unavailable on earlier machines. The system's performance contributed to the development of high-speed computing architectures that later influenced vector and parallel processing systems. Programming languages underwent rapid refinement during this period. Fortran 4, standardized in the mid-1960s, improved portability and consistency for scientific applications. COBOL evolved through international standardization committees to support expanding administrative tasks. ALGOL continued influencing academic computing, particularly in algorithm development and structured programming concepts. The increasing complexity of software prompted the emergence of systematic approaches to programming, marking the early stages of software engineering as a formal discipline. Institutions recognized that software development required structured methodologies, documentation, and management practices. Conferences, technical papers, and industry guidelines began addressing software reliability, maintenance, and scalability. Time-sharing expanded significantly during these years and changed how organizations interacted with computers. Following early demonstrations such as MIT CTSS, additional systems emerged that supported simultaneous interactive access by multiple users. Projects such as the Dartmouth time-sharing system, developed beginning in 1964, allowed students and researchers to write and execute programs in BASIC, a language designed for ease of use. Time-sharing installations appeared at universities, research laboratories, and some corporate environments, increasing access to computing resources without requiring each user to secure exclusive system time. Through terminal access, users could edit programs, run calculations, and retrieve results in real time. This interaction changed computing from a batch-oriented process into an interactive, iterative activity. The proliferation of time-sharing helped create expectations for future multi-user systems and network connectivity. Advances in storage technologies further enhanced system capabilities. Disk drives became more reliable and more widely adopted. Magnetic tape remained the primary medium for large data storage, particularly for archival purposes, but disk-based systems increasingly supported active applications requiring rapid access. The IBM 2314, introduced in the mid-1960s, offered higher capacity and transfer rates than earlier models. Improvements in error detection and correction increased data reliability. These storage advances supported the expansion of database systems and large administrative applications, laying the foundation for future data processing architectures. The expansion of mainframe computing required growing numbers of trained personnel. Universities introduced programs in computer science, building on earlier mathematics and engineering curricula. The first department, named Computer Science, emerged in the early 1960s, reflecting recognition of computing as a distinct academic field. Governments and corporations invested in training programs for programmers, system operators, analysts, and maintenance technicians. Manuals, standards, and formal documentation practices became more important as systems grew in complexity and as organizations expanded their computing workloads. During this same period, integrated circuits began transitioning from laboratory devices to early commercial use. Although most mainframes still relied on transistor-based modules, specialized equipment in aerospace and military applications incorporated early integrated circuits for improved reliability and reduced size. Integrated circuits also appeared in instrument control systems, calculators, and communication devices. As semiconductor fabrication improved yields and reduced costs, integrated circuits became increasingly competitive with discrete transistor circuits. Their gradual introduction into commercial computers during the late 1960s marked a significant advance towards smaller and more powerful systems. Networking concepts advanced in parallel with time-sharing and mainframe development. Researchers explored methods for linking computers through communication lines to support resource sharing, file transfer, and distributed computing. Although full-scale computer networks were not yet established, experiments demonstrated that remote terminals could access central computers over telephone lines and that multiple computing sites could share information. These ideas provided the conceptual groundwork for the packet switching research that would emerge in the late 1960s. Mainframe applications expanded dramatically between 1963 and 1968. Governments used computers for census processing, taxation systems, military logistics, social security administration, and weather forecasting. Corporations expanded their use of computing for payroll processing, inventory management, financial analysis, and production planning. Banks increased their reliance on automated processing and electronic transaction systems. Airlines implemented computerized reservation systems, such as the Sabre system developed jointly by IBM and American Airlines. These applications demonstrated computing's value for large-scale data management and organizational coordination. International competition in computing intensified. Japan's computer industry advanced rapidly through domestic development and strategic licensing agreements. Companies such as NEC, Hitachi, and Fujitsu produced increasingly capable systems and gained experience in software development and systems integration. Western Europe advanced through firms like Siemens, ICL, and Bull, often supported by government initiatives aimed at strengthening domestic industries. The Soviet Union pursued high-performance computing for military and scientific applications, but faced constraints in semiconductor production and access to Western technology. Despite these challenges, Soviet research institutions produced systems capable of significant numerical computation. As computing expanded, concerns about software complexity, system reliability, and resource management became more prominent. Organizations recognized that hardware improvements alone could not resolve issues arising from poorly structured software or inadequate documentation. Conferences and publications during this period examined software development practices, leading to early formulations of software engineering principles. Although still in early stages, these discussions influenced later methodologies and contributed to the recognition of software as a critical factor in system performance and long-term viability. By 1968, computing had become firmly established within government, research, and commercial sectors. Mainframes operated in climate-controlled facilities across numerous countries. Time-sharing supported interactive computing for thousands of users. Universities trained professionals in computer science. Integrated circuits were beginning to enter commercial equipment. Storage capacity and processing speed continued to increase, and large-scale applications demonstrated computing's growing role in organizational functions. The period from 1963 to 1968 represents a decisive consolidation of computing power, system architecture, and institutional reliance on digital technology. The introduction of IBM's System/360 established architectural unification. The rise of supercomputing expanded capabilities in scientific research. Time-sharing opened computing to wider audiences. Advances in software, storage, and semiconductor technology positioned computing for further integration into industrial and administrative systems. These developments created the technological and institutional environment essential for subsequent breakthroughs in networking, microprocessors, and digital automation. The Third Industrial Revolution advanced significantly during this period, setting the stage for the transformations that unfolded in the late 1960s and early 1970s. 1969 to 1972 marked the transition from isolated computing systems to the first operational computer network capable of transmitting data between geographically separated machines. This development emerged from research programs funded by the United States Department of Defense, particularly through the Advanced Research Projects Agency. The resulting network, known as ARPANET, served as the first large-scale implementation of packet switching, a method of dividing data into discrete units for transmission. This development established the foundation for future global networks, including the modern Internet. The ARPANET's formation occurred alongside advances in time-sharing, computing hardware, software engineering, and telecommunications, creating a technological environment suitable for networked communication. The origins of ARPANET trace to the early 1960s, when researchers recognized the limitations of isolated computing systems. Time-sharing had demonstrated that multiple users could access a central computer through terminals, but computing resources remained confined to local environments. The United States defense research community sought methods to allow computers at different research sites to share information and computational resources. In 1962, J.C. R. Licklider, serving as director of ARPA's Information Processing Techniques Office, promoted the concept of an interconnected network of computers that would enable communication among geographically distributed researchers. His vision emphasized resource sharing, collaboration, and distributed computation. Although Licklider left ARPA after a short tenure, his ideas influenced subsequent research programs. Leonard Kleinrock's work on queuing theory at MIT in the early 1960s provided mathematical foundations for packet switching. Traditional telecommunications systems relied on circuit switching, which reserved continuous communication paths for voice or data between endpoints. Packet switching broke data into independent packets routed individually through the network, improving efficiency and resilience. Paul Barron at Rand Corporation and Donald Davies at the National Physical Laboratory in the United Kingdom independently explored packet switching concepts during the 1960s. These developments supported ARPA's decision to implement a packet switch network rather than a circuit switch system. By 1967, ARPA initiated planning for a national experimental computer network. Lawrence Roberts, who joined ARPA after working at MIT's Lincoln Laboratory, led the early design efforts. The agency sought a contractor to build the Interface Message Processors, IMPs, specialized mini-computers that would manage data transmission between host computers and the network. After reviewing proposals, ARPA awarded the contract to Bolt, Beranek, and Newman, a research-oriented engineering firm with experience in advanced computing projects. BBN engineers designed the IMPs around Honeywell DDP 516 mini-computers equipped with additional memory and customized communication interfaces. The IMPs would function as packet switching nodes, routing data among host systems without requiring modifications to the hosts themselves. The first ARPANET node became operational at the University of California, Los Angeles, on September 2, 1969. This installation connected UCLA's SDS Sigma 7 computer to the first IMP. In October 1969, a second node was installed at Stanford Research Institute, linking its SDS 940 timesharing system. On October 29, 1969, the first host-to-host communication occurred when UCLA attempted to log into SRI's computer. The first message transmitted consisted of the letters "LO" as the system crashed before completing the intended command login. Despite the interruption, the event demonstrated successful communication between remote computers. Additional nodes were established later that year at the University of California, Santa Barbara, and the University of Utah, forming the initial four-node ARPANET. The network expanded steadily in 1970 and 1971 as additional research institutions joined. The installation of IMPs created a growing packet switching infrastructure across the United States. By 1971, the network included more than a dozen nodes, linking universities, government laboratories, and contractor facilities. The IMPs handled packet routing, error checking, congestion control, and connection management, while host computers implemented higher-level protocols to communicate with the IMPs. This division between host responsibilities and network responsibilities became a central architectural principle of modern networking. A major step occurred in 1971 with the introduction of networked electronic mail. Ray Tomlinson at BBN implemented an experimental program that allowed users to send messages between computers connected to ARPANET. He selected the symbol to separate usernames from host identifiers, establishing a convention still used today. Although initially a secondary function within file transfer utilities, electronic mail quickly became one of the most widely used features of ARPANET. It demonstrated the value of digital communication for rapid information exchange and influenced the long-term development of network services. The development of network protocols was essential for ARPANET's function. Early communication procedures, known as the Network Control Protocol, provided a method for establishing and managing connections between host computers. NCP enabled file transfer, remote login, and messaging capabilities. Although limited compared to later networking protocols, NCP represented the first operational host-to-host communication system used on a large-scale packet switching network. Subsequent refinements improved reliability, throughput, and compatibility. These developments established the conceptual basis for the transmission control protocol and Internet protocol that emerged later in the 1970s. Telecommunications infrastructure played a crucial role in enabling ARPANET's expansion. Dedicated communication lines leased from national telephone carriers connected IMPs across long distances. These lines operated at speeds such as 50 kilobits per second, which, while modest by later standards, represented significant capacity for the period. The reliability of these lines influenced network stability and performance. ARPA and BBN collaborated closely with telecommunications carriers to maintain consistent service and reduce downtime. These early experiences with leased line reliability informed later network design decisions and highlighted the need for redundancy and adaptive routing. The expansion of ARPANET influenced research practices at participating institutions. Remote terminal access allowed researchers to use computing resources located across the network rather than relying solely on local systems. File transfer capabilities supported collaborative programming, data sharing, and distributed problem solving. The network facilitated communication among researchers working on similar projects, reducing duplication of effort and accelerating the pace of innovation. ARPANET became an essential tool for communities engaged in artificial intelligence, computer graphics, operating systems research, and formal methods. International developments paralleled ARPA's efforts. Donald Davies and colleagues at the National Physical Laboratory in the United Kingdom implemented an experimental packet switching network that influenced ARPA's design decisions. Research groups in France initiated preliminary work that later contributed to national data networks. These efforts demonstrated global interest in packet switching and distributed computing. Although ARPANET became the most extensive early network, it operated within an international environment exploring similar concepts. ARPANET raised significant organizational and administrative considerations. Network governance required coordination among universities, government agencies, and contractors. ARPA established guidelines for system operation, research priorities, and acceptable use. Technical teams at participating institutions collaborated to maintain host software compatibility and network stability. System logs, error reports, and performance measurements informed protocol revisions and hardware improvements. These practices laid the groundwork for future network administration methods. By 1972, ARPANET had expanded to more than 20 nodes and was integrated into research and administrative workflows across numerous institutions. A major demonstration took place in October 1972 at the International Computer Communication Conference in Washington, D.C., where participants showcased network applications including electronic mail, remote login, and file transfer. This event marked the first public presentation of ARPANET to a large technical audience and demonstrated the feasibility of packet switching for general communication. The developments between 1969 and 1972 established foundational principles that guided later network design. Packet switching demonstrated superior efficiency and resilience compared to circuit switching for digital data. Host-to-host protocols provided a method for structured communication between heterogeneous systems. Leasing communication lines from carriers revealed the operational challenges of wide-area networking and influenced designs for fault tolerance and flexible routing. Electronic mail demonstrated the potential of digital communication for rapid information exchange. ARPANET's formation also demonstrated the importance of collaborative research efforts. Universities, government agencies, and private contractors contributed expertise in computing, communication, hardware design, and software engineering. This collaboration allowed rapid development of standards, protocols, and operational practices. The network's success encouraged continued investment in networking research, leading to additional projects that expanded the scope and ambition of digital communication. By the early 1970s, ARPANET had proven that distributed computing environments could function effectively. The network supported remote login, file transfer, messaging, and resource sharing across multiple institutions. These capabilities represented the earliest form of large-scale digital communication systems. ARPANET's architecture and operational experiences influenced subsequent networks in the United States and abroad. The principles established during this period formed the foundation for future developments in inter-network communication, leading eventually to the emergence of the global Internet. From 1970 to 1975 marks a major transformation in digital technology as microprocessors emerged and semiconductor manufacturing advanced toward large-scale and very large-scale integration. These developments reshaped computing by enabling compact, efficient processing units that could be incorporated into a wide range of devices. Microprocessors, supported by improved memory technologies, refined semiconductor fabrication, and expanding design methods, reduced the size and cost of electronic systems and positioned computing for broader commercial and industrial adoption. This period established the fundamental architecture of modern computing and accelerated the transition from large institutional systems to personal, embedded, and distributed computing environments. The invention of the microprocessor resulted from the convergence of semiconductor scaling, circuit integration, and growing demand for programmable control systems. By the late 1960s, integrated circuits had progressed from small-scale integration, containing a few components, to medium-scale integration, supporting dozens or hundreds of components on a single chip. This increase in density made it feasible to combine arithmetic logic, registers, and control circuitry into a unified processing device. Early projects sought to replace complex board-level designs in calculators and control systems with single-chip solutions that reduced cost and simplified engineering. The first commercially available microprocessor was the Intel 4004, introduced in 1971. It originated from a contract with Bizicom, a Japanese calculator manufacturer seeking a set of custom integrated circuits for a programmable calculator. Intel engineers, including Martian Hoff, Federico Faggin, and Stanley Mazur, proposed replacing multiple custom chips with a general-purpose 4-bit processor capable of executing instructions stored in memory. The resulting 4004 contained approximately 2,300 transistors, operated at clock speeds up to 740 kHz, and supported basic arithmetic and control functions. Although limited in capability, the 4004 demonstrated that a programmable logic device could be implemented on a single chip. It marked the shift from specialized integrated circuits to general-purpose microprocessors. Intel expanded this capability with the 8008 in 1972 and the 8080 in 1974. The 8008, an 8-bit processor, contained around 3,500 transistors and supported more extensive instruction sets, but required complex support circuitry. The 8080 improved performance significantly, with approximately 6,000 transistors and faster processing speeds. It became one of the most influential early microprocessors because of its versatility and expanding ecosystem of support components. The 8080's design allowed engineers to build increasingly capable computing systems without relying on large-scale hardware assemblies. Although the 8080 predated widespread adoption of personal computers, it provided the core technology upon which many later systems were built. Other companies contributed to early microprocessor development. Texas Instruments introduced the TMS 1000 in 1974, one of the earliest microcontroller units integrating a processor, read-only memory, and random access memory on a single chip. Motorola developed the MC6800, released in 1974, which provided an alternative architecture and influenced subsequent designs. Japanese semiconductor firms expanded production capacities during this period and licensed or developed microprocessor technologies to support domestic electronics industries. These developments demonstrated a global shift toward programmable integrated circuits and established the foundations for diversified microprocessor markets. Semiconductor fabrication techniques advanced rapidly between 1970 and 1975. Photolithographic resolution improved, allowing finer circuit geometries and higher component densities. Ion implantation techniques enhanced doping precision. Oxidation and metallization processes improved reliability. These advancements increased yields and reduced costs, making microprocessors and memory chips more economically viable for commercial applications. The semiconductor industry began transitioning from medium-scale to large-scale integration, enabling the production of chips with thousands of transistors. Although the full transition to very large-scale integration would occur later in the decade, the groundwork was established during these years. Memory technologies advanced alongside microprocessors. Dynamic random access memory improved capacity and speed, with early drum chips such as the Intel 1103, introduced in 1970, demonstrating the feasibility of replacing magnetic core memory in many applications. The 1103 stored 1,024 bits per chip and although modest by later standards, it represented a major step towards semiconductor memory systems. DRAM offered a smaller size, lower power consumption, and higher potential density compared to magnetic core memory. Read-only memory devices also improved, allowing microprocessors to store firmware and control programs efficiently. These memory developments supported the integration of microprocessors into increasingly sophisticated systems. The emergence of microprocessors influenced numerous industries. In consumer electronics, microprocessors enabled advanced calculators, digital watches, and early home appliances with programmable features. In industrial control, microprocessors supported automated machinery, monitoring systems, and process controllers with improved precision and reduced component counts. Telecommunications equipment incorporated microprocessors to manage switching functions and network control tasks. The automotive industry began exploring microprocessor-based engine control units to regulate fuel injection and ignition timing. These early applications demonstrated microprocessors' potential to provide flexible, compact, and programmable control across multiple sectors. The period also saw the emergence of early development systems and design tools. Engineers required assemblers, simulators, and hardware interfaces to build software and hardware around microprocessors. Companies such as Intel and Motorola introduced development kits that provided programmers with the tools needed to experiment with instruction sets, memory configurations, and peripheral devices. These systems assisted engineers in designing new products and contributed to the growth of microprocessor-based innovation. Microprocessor adoption required new approaches to software development. Assembly language programming became central to early microprocessor applications due to limited memory and processing capability. Software for embedded systems had to be tightly optimized, requiring detailed knowledge of processor architecture and timing. Documentation practices improved, and early software guidelines emerged to support reliable programming. These experiences influenced later developments in embedded systems engineering and contributed to the broader evolution of software engineering as a discipline. As microprocessors became more capable, their influence extended to computing architectures. Designers began exploring the concept of microcomputers, small systems built around microprocessors, memory, and peripheral interfaces. Early experimental systems demonstrated that microprocessor-based computers could support general computation tasks traditionally reserved for larger machines. These developments set the stage for personal computing, single-board computers, and educational systems that would emerge later in the decade. International competition intensified as semiconductor capabilities expanded. The United States led microprocessor innovation due to early investments in semiconductor research and strong industry, government collaboration. Japan expanded fabrication capacity and supported its electronics industry through long-term industrial policy. Western European firms advanced semiconductor design and production, but faced challenges in scaling manufacturing to match the United States and Japan's output. The Soviet Union pursued microprocessor development, but encountered difficulties due to limited access to Western fabrication technologies and slower progress in integrated circuit production. Despite these differences, all major industrial regions recognized microprocessors' transformative potential and invested accordingly. Microprocessors influenced research fields beyond commercial and industrial applications. Robotics research explored the integration of microprocessor-based controllers to support more flexible movement sequences and improved sensor processing. Laboratory instrumentation incorporated microprocessors to manage measurement timing, calibration routines, and data logging. Early digital communication experiments used microprocessors to manage signal processing tasks. Each of these developments demonstrated microprocessors' expanding functional scope. Microprocessors also affected economic structures. As production costs decreased, industries adopted microprocessor-based systems to replace mechanical or analog controls. Manufacturers benefited from flexible programming, reduced inventory of specialized components, and simplified hardware designs. Microprocessors enabled iterative product updates through software changes rather than complete hardware redesigns. These economic advantages reinforced the shift toward digital systems and increased demand for semiconductor components, contributing to rapid growth in the global semiconductor market. By 1975, microprocessor technology had progressed to the point where compact computing systems were feasible for hobbyists, researchers, and specialized applications. The Altair 8800, introduced in late 1974 and becoming widely known in early 1975, used the Intel 8080 and demonstrated that microprocessor-based systems could support general computation. Although primitive by later standards, the Altair influenced the emergence of early personal computing and illustrated microprocessors' potential beyond embedded control. Its appearance signaled the beginning of broader microcomputer experimentation that would accelerate in subsequent years. The developments from 1970 to 1975 formed the technological core of modern digital systems. Microprocessors established a programmable processing architecture that could be scaled, adapted, and incorporated into a vast range of devices. Semiconductor manufacturing advances supported increased complexity and reduced cost. Memory technologies enabled practical digital storage. Early applications demonstrated microprocessors' utility across industrial, consumer, and research environments. These innovations collectively set the stage for the personal computing revolution, continued automation, and the expansion of digital electronics into all sectors of society. The 1970s represent a period of accelerated automation as industrial robotics, computerized control systems, and advanced manufacturing techniques expanded across global industries. Building on developments from the early 1960s, automation matured into a major technological and economic force. During this decade, robotic systems became more capable, numerical control evolved into computer numerical control, and manufacturing processes became increasingly integrated with digital systems. These developments reshaped industrial productivity, labor structures, and competitive dynamics among the world's leading manufacturing nations. The 1970s established automation as a central pillar of industrial modernization and positioned robotics as a key factor in international economic competition. Industrial robotics expanded significantly during this period. Following the initial deployment of Unimate robots in the early 1960s, the 1970s saw widespread experimentation and adoption. Robots became increasingly capable due to improvements in sensors, actuators, control logic, and reliability. Early robots performed tasks such as welding, painting, material handling, and machine loading. Hydraulic and pneumatic actuators continued to dominate, but electric motor-driven systems gained ground due to improved precision and easier integration with electronic control units. Robot repeatability and payload capacity increased, allowing deployment in more demanding industrial environments. By the mid-1970s, robots were incorporated into assembly lines for automobiles, appliances, and machinery components. Computer numerical control, CNC, emerged as a major development during this decade. CNC replaced punch tape instructions with digital commands executed by microprocessor-based controllers, allowing greater flexibility, accuracy, and automation. These systems supported storage and retrieval of machining programs, dynamic adjustment of feed rates, and real-time monitoring of tool performance. CNC machines delivered tighter tolerances, reduced setup times, and improved consistency across production cycles. Machine tool manufacturers integrated microprocessors, memory modules, and digital sensors into equipment, enabling advanced automated machining with minimal direct operator intervention. CNC spread rapidly into industries requiring precision manufacturing, contributing to standardized components and improved product quality. Japan became a leading nation in industrial automation during the 1970s. Government programs, coordinated through long-term industrial policy, supported research, training, and investment in robotics and precision manufacturing. The Ministry of International Trade and Industry issued planning documents outlining the strategic importance of automation for industrial competitiveness. Japanese companies such as Fanuc, Kawasaki, Hitachi, Yaskawa, and Mitsubishi developed robotic systems and CNC equipment suited for large-scale manufacturing environments. By the late 1970s, Japan had surpassed the United States in robot density, measured as installed robots per manufacturing worker. High growth in the automotive and electronics industries accelerated adoption, and Japanese producers integrated robots into assembly lines extensively to improve throughput and reduce defects. Western European countries also expanded automation capabilities. Germany invested heavily in precision machinery, robotics research, and automated assembly systems. German firms developed sophisticated CNC machines and robotic welding systems used in automotive manufacturing. Sweden, Italy, and the United Kingdom also contributed to robotics development, often supported by government modernization programs. European research institutions investigated advanced sensing systems, adaptive control algorithms, and robotic vision technologies. Although adoption patterns varied by country and industry, Europe maintained a strong industrial base and invested in high-quality machine tools and automated manufacturing. In the United States, automation expanded but faced structural challenges. American companies adopted robotics and CNC technology, particularly in automotive and aerospace sectors, but domestic manufacturing experienced competitive pressure from Japan and Western Europe. Some United States manufacturers relied on aging equipment and faced difficulties transitioning to more flexible automated systems. However, the United States remained strong in robotics research and development. Universities and laboratories conducted early work in robotic manipulation, artificial intelligence, base control, and machine vision. Companies such as Unimation continued producing industrial robots, and new firms explored advanced designs. Despite industrial restructuring, the United States industries maintained significant automation capacity and contributed to global technological development. The automotive industry illustrates the increasing importance of automation. Car manufacturers introduced robotic welding and paint systems to improve precision and reduce variability. These tasks required consistent application of materials, and robots delivered stable performance across high-volume production. Robotic welding systems reduced defects and improved structural integrity. Painting robots provided uniform coatings and reduced employee exposure to hazardous chemicals. Automation supported energy efficiency and improved environmental compliance by optimizing material usage and reducing waste. Advanced process industries also expanded automated control systems. Petrochemical plants, oil refineries, and steel mills adopted digital control computers to regulate continuous flow processes. Distributed control systems emerged during the 1970s, allowing multiple microprocessor-based units to manage specific tasks while coordinating through supervisory networks. These systems improved reliability and allowed finer control of temperature, pressure, and chemical composition. Automation in these sectors increased output consistency, reduced waste, and supported safer operation through real-time monitoring and rapid response mechanisms. Robotic technologies required advances in sensors and feedback systems. Position encoders, force sensors, and proximity detectors improved robotic accuracy. Industrial robots became increasingly programmable, allowing operators to adjust movement patterns and optimize performance for specific tasks. Early machine vision systems appeared in research settings, enabling robots to identify objects and perform rudimentary inspection tasks. Although commercial deployment of vision-guided robots remained limited during the 1970s, the foundational work conducted during this decade enabled major advancements in the following years. Automation influenced labor markets significantly. While automation did not eliminate large numbers of jobs during the early years of adoption, it altered skill requirements. Workers needed training in programming, equipment maintenance, and system oversight. Technical education expanded to meet demand for technicians and engineers capable of designing and operating automated machinery. Labor unions negotiated agreements concerning job security, retraining programs, and workplace safety. Nations with strong technical education systems adapted more efficiently to automation, while others faced adjustment challenges as traditional manufacturing roles evolved. Economic competition intensified as automation reshaped industrial productivity. Japan's rapid growth in robot adoption enabled high output levels, stable production quality, and reduced labor costs per unit. This contributed to Japan's increasing share of global automotive and electronics markets. Western European industries maintained strong performance through precision engineering and consistent investment in high-quality machine tools and manufacturing technology. The United States experienced competitive pressure but retained leadership in robotics research and semiconductor development, both essential for long-term industrial competitiveness. Semiconductor advances supported the expansion. Integrated circuits grew more powerful and affordable, enabling the inclusion of microcontrollers and digital processors in industrial machinery. Improvements in programmable logic, memory capacity, and sensor interfaces allowed robotics and CNC systems to operate with greater precision. Semiconductor scaling resulted in higher reliability and reduced component size, essential for complex control circuitry. Automation and semiconductor technologies reinforced each other. As integrated circuits improved, automation systems became more capable, and the need for automation further increased demand for advanced semiconductors. Automation also transformed quality assurance and inspection. Automated inspection systems used sensors, gauges, and digital logic to verify product dimensions and detect defects. These systems improved feedback loops in manufacturing, enabling rapid correction of deviations and contributing to statistical process control methods. As industries applied automation more comprehensively, defect rates decreased and product consistency improved. These changes reinforced the competitive advantages of nations investing heavily in automation technology. International standards organizations began addressing robotics and automation during the 1970s. Technical committees defined terminology, safety practices, and performance metrics for industrial robots and CNC equipment. These standards supported international trade in machinery, allowed clearer comparison of capabilities, and promoted interoperability among equipment types. Standardization contributed to stable growth by ensuring consistency in equipment performance and enabling manufacturers to adopt automation with reduced uncertainty. The adoption of automation and robotics influenced factory layout and workflow design. Automated systems encouraged linear production flows, reduced handling time, and minimized bottlenecks. Factories reconfigured assembly lines to accommodate robotic workstations. Storage and retrieval systems became more systematic, and just-in-time production principles developed in Japan aligned well with automated processes. These changes raised productivity and supported flexible manufacturing capable of adapting to shifts in demand. By the late 1970s, robotics and automation had become central components of industrial modernization. Japan led in robot deployment and precision manufacturing. Western Europe maintained strong engineering capabilities and invested in advanced automation technologies. The United States contributed major research and retained significant industrial capacity while undergoing structural adjustments. Automation expanded across consumer electronics, automotive, aerospace, steelmaking, petrochemicals, and machining industries. The combined influence of robotics, CNC systems, and digital process control defined the industrial landscape and prepared the way for further technological integration. The developments of the 1970s established automation as a defining feature of the Third Industrial Revolution. Robotics and CNC technologies delivered higher productivity, improved product quality, and greater consistency. Distributed control systems in advanced process industries. Semiconductor improvements supported more powerful and compact control units. Global competition intensified as nations adopted automation at different rates, influencing industrial output and economic balance. The technological and institutional foundations laid during this decade shaped industrial production for the following decades and formed a crucial part of the broader digital transformation. The period from 1973 to 1979 marks a significant intersection between energy systems and technological development during the Third Industrial Revolution. The two major oil shocks of the decade exposed vulnerabilities in global energy supply, altered geopolitical relationships, and forced industrial economies to reconsider their dependence on petroleum. These disruptions accelerated the adoption of nuclear power, stimulated early investment in renewable energy technologies, and reshaped industrial production through increased focus on energy efficiency. The events of these years transformed long-term technological strategies and influenced the evolution of digital, mechanical, and industrial systems. The first oil crisis began in October 1973 when members of the Organization of Arab Petroleum Exporting Countries imposed an embargo on nations supporting Israel during the Yom Kippur War. Oil prices rose sharply, increasing from around $3 per barrel to more than $12 by early 1974. The magnitude of this increase strained industrial economies heavily dependent on imported petroleum. High fuel costs disrupted transportation, manufacturing, and electricity generation. The embargo highlighted the strategic role of oil in global economic and industrial systems and exposed the risks associated with concentrated supply sources. Industrial economies responded by implementing measures to reduce energy consumption and diversify supply. Governments established energy ministries, created strategic stockpiles, and introduced policies promoting energy efficiency. Industries adopted improved insulation, heat recovery systems, and more efficient combustion technologies. Companies restructured production processes to reduce energy-intensive operations. The crisis accelerated research on alternative energy technologies and encouraged long-term planning for reduced dependence on imported oil. Nuclear power emerged as a primary alternative energy source during this period. In the United States, Western Europe, Japan, and the Soviet Union, governments expanded nuclear development programs to increase electricity supply stability. Nuclear reactors offered high output levels, reduced sensitivity to petroleum price fluctuations, and potential long-term cost advantages. Several countries approved the construction of new reactors, and existing programs accelerated. Pressurized water reactors and boiling water reactors became the predominant designs. France, through a coordinated national energy policy, initiated a large-scale nuclear program that would eventually make nuclear power the dominant source of French electricity. Japan expanded its nuclear capacity to support rapid industrial growth while reducing dependence on imported oil. The United States continued construction of civilian reactors, although public debate and regulatory changes later slowed expansion. The Soviet Union maintained a broad reactor development program, serving both civilian and strategic needs. Western European nations, including Germany, Sweden, Belgium, and the United Kingdom, invested in nuclear facilities to support industrial demand. These developments marked one of the largest coordinated periods of nuclear expansion in modern history. The oil crisis also influenced industrial modernization. High manufacturing energy costs encouraged the adoption of more efficient processes, materials, and technologies. Automation systems incorporated energy monitoring functions, allowing more precise control of process variables that influence consumption. Factories upgraded their heating, cooling, and ventilation systems. Industries reduced their reliance on energy-intensive materials, such as certain metals, by adopting alternatives where feasible. These adjustments demonstrated the growing integration of energy management with industrial engineering. The second oil shock occurred in 1979 following the Iranian Revolution, which disrupted oil production and contributed to another sharp rise in prices. Oil costs have more than doubled, placing additional pressure on industrial economies already adjusting to the effects of the first crisis. The second shock reinforced the strategic necessity of diversification, efficiency, and long-term energy planning. Governments strengthened conservation policies, expanded energy taxation structures, and increased support for alternative technologies. Renewable energy research advanced meaningfully during this decade. Although far from commercial maturity, solar, wind, and geothermal technologies received increased funding and policy support. The United States established research institutes and demonstration programs examining photovoltaic systems, and solar thermal applications. Western European countries invested in wind turbine research, with Denmark developing early prototypes that influenced later commercial designs. Japan explored solar water heating systems for residential and commercial use. These early steps formed the initial phase of renewable energy technology development, laying the groundwork for more advanced systems in subsequent decades. Hydroelectric power also saw expansion in regions with suitable geography. Large-scale projects increased generating capacity and provided alternatives to fossil fuel-based electricity. Although hydroelectric technology itself was well established, increased investment during this period reflected broader efforts to diversify renewable and low-carbon energy sources. The integration of hydroelectric power into national energy strategies contributed to more resilient energy supply structures. Energy crises influenced the transportation and automotive industries significantly. Rising fuel prices encouraged the development of more efficient engines, lighter vehicle materials, and improved aerodynamics. Automotive companies introduced vehicles with reduced engine displacement and improved fuel economy. Governments implemented standards requiring higher efficiency, influencing engineering decisions and accelerating innovation in engine control technologies. Microprocessors, emerging in the early 1970s, supported electronic fuel injection and ignition control systems that enhanced combustion efficiency. These early systems formed the basis for more sophisticated automotive electronics that would develop in later decades. In industrial manufacturing, increased energy costs encouraged the adoption of variable speed motor drives, improved insulation in furnaces and kilns, and optimized scheduling of energy-intensive processes. The introduction of digital process control systems allowed for more precise energy management, reducing waste. Industries implemented cogeneration systems that captured waste heat for secondary use. These measures demonstrated that energy crises reinforced the role of automation and digital control in industrial modernization. Telecommunications and computing industries were also affected indirectly. Increased energy costs reinforced the need for efficient cooling in data centers and computing facilities. Manufacturers explored reduced power circuits and optimized board designs. Although progress in low-power semiconductor design remained limited during this decade, the broader emphasis on efficiency influenced long-term research directions. Increased awareness of energy constraints supported interest in compact, efficient electronic systems that would become more important in later stages of the digital revolution. Geopolitical relationships shifted as energy security became a central strategic concern. Oil-producing nations increased their influence in global affairs, while industrial nations sought new alliances and supply arrangements. The International Energy Agency, established in 1974, coordinated policy responses among industrial nations, managed shared reserves, and provided analysis of energy markets. This institutional structure reflected recognition that energy availability was fundamental to industrial and technological stability. It also influenced decisions about strategic investment in nuclear, renewable, and efficient technologies. Industrial policy evolved significantly in response to energy concerns. Several nations introduced subsidies for energy-efficient equipment, tax incentives for alternative energy research, and regulations limiting consumption in specific sectors. Standards organizations developed guidelines for appliance efficiency, building insulation, and industrial equipment performance. These measures established energy efficiency as a long-standing component of industrial policy. The energy crisis also influenced public perception of technology and industrial development. Although public opinion did not directly shape industrial policy in many regions, the visible effects of fuel shortages and rising costs increased attention to energy technologies and infrastructure. Some nations experienced debate about nuclear safety, environmental impacts, and long-term waste management. These concerns influenced regulatory frameworks for reactor construction and operation. As nuclear programs expanded, safety standards, inspection procedures, and operational protocols became more formalized. By the late 1970s, the combination of nuclear expansion, early renewable development, increased efficiency, and industrial restructuring had significantly altered energy landscapes in industrial economies. Nuclear capacity had grown substantially, particularly in France, Japan, and the United States. Renewable energy research had produced early prototypes and demonstration systems that formed the basis for later commercialization. Industrial processes had become more efficient through automation, material changes, and optimized energy use. The automotive industry had redesigned vehicles for improved efficiency, incorporating early electronic control systems. Governments had institutionalized energy planning through agencies, standards, and long-term strategies. The developments from 1973 to 1979 demonstrate how energy crises influenced the trajectory of the Third Industrial Revolution. The increased cost of energy accelerated the adoption of digital control systems, stimulated research on alternative energy sources, and promoted technological changes that reduced energy intensity. Nuclear power expanded rapidly, providing high-output electricity to support industrial modernization. Renewable technologies began their initial phase of development. These changes shaped industrial strategies, influenced geopolitical alignments, and set the stage for long-term diversification of global energy systems. The years from 1980 to 1985 represent a decisive shift in the trajectory of the Third Industrial Revolution, as computing moved from institutional environments into homes, small businesses, and classrooms. This period marks the transition from specialized, large-scale computing systems to widespread personal computing. Several converging factors enabled this transformation. Advances in microprocessor technology, reduced costs of memory and storage, development of user-friendly operating systems, and expansion of software markets. By the mid-1980s, personal computers had become a significant sector of global technology markets and reshaped the relationship between individuals and digital systems. Personal computing emerged gradually during the late 1970s with systems such as the Apple II, Commodore PET, and Tandy TRS-80. These early microcomputers demonstrated that general-purpose computing could be achieved using microprocessors, semiconductor memory, and relatively simple operating environments. By 1980, these systems had established a market for hobbyists, educational institutions, and small businesses. Microprocessors such as the MOS 6502, Zilog Z80, and Intel 8080 provided adequate processing power for applications, including word processing, numerical analysis, and simple graphics. However, the early market remained fragmented, with systems differing in architecture, software compatibility, and hardware design. The introduction of the IBM personal computer in August 1981 altered the landscape substantially. IBM's entry into the personal computer market provided credibility and standardization that the sector had previously lacked. The IBM PC used the Intel 8088 microprocessor, a variant of the 8086 with an 8-bit external data bus, enabling lower system costs while maintaining compatibility with 16-bit software. IBM's design emphasized modularity, allowing easy expansion through standardized internal slots. The use of off-the-shelf components simplified manufacturing and encouraged third-party development of peripherals and compatible systems. The IBM PC ran PC-DOS, developed by Microsoft, which provided a command-line environment supporting file management, program execution, and disk operations. IBM's marketing and distribution networks ensured broad visibility and adoption. Within months, the IBM PC became a dominant platform in business computing. Its open architecture encouraged other manufacturers to develop compatible systems, known as IBM PC clones, which expanded the market and lowered hardware costs. Companies such as Compaq and Columbia Data Products introduced compatible systems that matched IBM's specifications, accelerating diffusion and increasing competitive pressure. Apple Computer pursued a distinct approach to personal computing. In January 1984, Apple introduced the Macintosh, a system based on the Motorola 68000 microprocessor. The Macintosh incorporated a graphical user interface, menu-driven interactions, and a desktop metaphor supported by a mouse. These features reduced reliance on memorized commands and made computing more accessible to users without technical backgrounds. Although the Macintosh initially offered limited memory and storage compared to some competitors, its interface influenced long-term design trends in personal computing. The system's bundled applications demonstrated the value of graphical environments for word processing, drawing, and layout tasks. Software development expanded rapidly between 1980 and 1985. The availability of widely adopted hardware platforms encouraged programmers to create applications for business, education, and personal use. Word processors such as WordStar and later Microsoft Word supported document creation. Spreadsheet programs, beginning with VisiCalc and followed by Lotus 123, transformed financial analysis and business planning by enabling complex calculations on personal computers. Database programs provided tools for managing records and information. Programming languages such as BASIC, Pascal, and C allowed users and developers to write software tailored to specific needs. This expansion of software demonstrated that personal computers could support a wide range of productive tasks. Memory and storage technologies improved significantly during this period. Dynamic random access memory increased in capacity, reducing the cost of memory upgrades. Floppy disk drives became standard for software distribution and data storage, replacing cassette-based systems. Early hard disk drives entered the personal computer market, offering higher capacity and faster access times. Display technology improved, with color monitors and higher resolution graphics becoming more accessible. Peripheral devices such as printers, modems, and graphics tablets expanded system capabilities. These improvements supported more complex applications and increased the utility of personal computers across industries. Computer networking also began to influence personal computing. While large-scale networks such as ARPANET were still limited to research institutions, local area networks emerged in office environments. Ethernet and token ring networks supported shared file access, centralized printing, and early forms of electronic communication. Modems allowed individuals to connect to bulletin board systems and early online services, enabling remote information exchange. Although limited in speed and scope, these developments introduced the concept of digital connectivity outside institutional settings and prepared users for broader networking in later decades. International developments in personal computing followed varied trajectories. The United States remained the center of innovation and market expansion due to its strong semiconductor and software industries. Japan produced competitive systems through companies such as NEC, Fujitsu, and Sharp. NEC's PC 8801 and PC 9801 series became dominant in the Japanese market, supporting domestic software ecosystems and business applications. Western Europe developed personal computing systems for educational use, including the BBC Micro in the United Kingdom, produced by Acorn Computers, which influenced computer literacy programs. European markets also saw systems from Amstrad and Sinclair, representing cost-effective options for home computing. Although fragmentation remained a factor in international markets, global adoption increased steadily. The spread of personal computing influenced education significantly. Schools and universities introduced computer literacy programs that used personal computers for teaching programming, mathematics, and general digital skills. Students learned basic and other entry-level languages. Computer labs supported coursework across engineering, sciences, and business disciplines. These educational developments contributed to a generation familiar with digital systems and prepared the workforce for the increasing digitalization of industry and administration. Personal computing also altered organizational workflows. Businesses used personal computers for word processing, financial modeling, inventory management, and communication. Adoption enabled decentralization of computing tasks that previously required mainframe time. Departments and individuals gained autonomy in managing information and performing computational tasks. Companies implemented local networks and shared resources, increasing efficiency and improving information flow. The shift from centralized data processing to distributed personal computing reflected broader trends in organizational structure and information management. Semiconductor technology continued advancing during this period, supporting more powerful microprocessors for personal computing. The Intel 8086, introduced in 1978, and its variants, including the 8088 used in the IBM PC, supported wider address spaces and more sophisticated software. Motorola's 68000 series provided higher performance and influence systems such as the Macintosh and workstation-class computers. Zilog's Z8000 and improved versions of the Z80 extended capabilities for various markets. These developments demonstrated the increasing performance of microprocessors and allowed personal computers to support more demanding applications. Graphics and sound capabilities improved significantly. Early personal computers supported low-resolution graphics, but advances in display adapters enabled higher-resolution text and graphical modes. Systems used graphic standards such as CGA, MDA, and later EGA to support business and creative applications. Sound capabilities expanded beyond simple tones to include more complex audio output, supporting educational and entertainment software. These improvements broadened computing's appeal and enabled new categories of applications. The period also saw the development of portable computing. Early portable systems, such as the Osborne one introduced in 1981, demonstrated that personal computers could be made transportable, though they remained bulky by later standards. The Compact Portable, released in 1983, offered IBM PC compatibility in a portable form and contributed to the expansion of mobile computing markets. Although battery-powered laptops were not yet widespread, these early systems demonstrated demand for computing outside fixed locations. Personal computing influenced consumer behavior and market structures. Software publishing became a major industry as companies produced applications for business and home use. Retail distribution networks expanded to include dedicated computer stores. Magazines, instruction manuals, and reference guides supported new users. The availability of affordable personal computers increased interest in digital technology among the general public, marking the beginning of mainstream digital culture. By 1985, personal computing had become an established component of global technology development. IBM-compatible systems dominated large segments of the business market. Apple maintained influence through graphical interfaces and design innovations. Japanese and European systems served domestic markets and educational institutions. Software ecosystems supported a wide range of applications. Memory, storage, and display technologies continued to improve. Networking had begun entering office environments, and portable systems introduced early forms of mobile computing. The developments between 1980 and 1985 represent a major transition in the Third Industrial Revolution. Personal computing shifted digital technology from specialized institutions to broad public use. Hardware standardization, software expansion, improved peripherals, and reduced costs increased accessibility. Organizations decentralized computing functions, individuals gained new capabilities, and education systems integrated digital literacy into their curricula. These changes established personal computing as a fundamental platform for future digital developments, including the expansion of networking, mobile devices, and interactive software in subsequent decades. Personal computing, therefore, occupies a key position in the broader history of digital transformation. The emergence of user-oriented systems, widespread software markets, and affordable hardware altered the trajectory of technological development. The 1980s represent a major restructuring of global communication systems as telecommunications infrastructure transitioned from analog to digital technologies. During this decade, fiber optic networks, digital switching systems, satellite communication, and early mobile telephony expanded rapidly. These developments increased bandwidth, improved reliability, and reduced the cost of transmitting information. Telecommunications modernization created the foundation for the data networks, mobile systems, and global connectivity that characterized later stages of the Third Industrial Revolution. By the end of the 1980s, digital communication had become essential for corporate operations, government administration, scientific research, and international economic activity. The decade began with ongoing improvements in long-distance communication networks. Analog microwave relay systems and coaxial cable networks remained important, but digital alternatives expanded quickly. Fiber optic communication emerged as a transformative technology. Experiments in the 1970s demonstrated that light transmitted through glass fibers could carry significantly more data than electrical signals transmitted through copper lines. Throughout the early 1980s, telecommunications companies in the United States, Western Europe, and Japan deployed the first commercial fiber optic links. These early systems supported transmission rates in the hundreds of megabits per second, far exceeding the capacity of traditional copper-based infrastructure. Fiber optic systems offered several advantages. They provided higher bandwidth, lower signal attenuation, increased resistance to electromagnetic interference, and improved security against eavesdropping. Advances in semiconductor lasers, photodiodes, and low-loss optical fibers supported rapid adoption. By the mid-1980s, major inner-city routes incorporated fiber optics, and network planners recognized that optical communication would become the dominant long-distance transmission method. The transition to fiber optics facilitated the expansion of digital communication services, including high-speed data transfer and broadband networks. Digital switching represented another significant development in telecommunications modernization. Traditional electromechanical switches, which had provided reliable service for decades, lacked the speed and flexibility required for growing communication demands. Digital switching systems used microprocessor-based control units and solid-state components to route calls and manage network traffic. These systems improved connection speed, increased capacity, and supported advanced services such as call forwarding, conference calling, and early forms of data communication. By the late 1980s, digital switching had replaced large portions of analog switching equipment in industrialized countries, forming a more efficient and adaptable communication infrastructure. Mobile telephony experienced its first major expansion during this decade. Japan introduced the world's first commercial cellular system in 1979, and mobile networks expanded into Western Europe and the United States in the early 1980s. First-generation cellular networks, known as 1G systems, used analog modulation techniques and operated in the 800 to 900 MHz frequency range. Although limited in capacity and audio quality compared to later systems, 1G networks demonstrated the practicality of cellular communication. Subscriber numbers increased steadily as network coverage expanded and equipment costs decreased. Mobile phones remained relatively large and expensive during the early 1980s, but rapid technological progress produced smaller, more portable devices by the end of the decade. Satellite communication has also advanced significantly. Geostationary satellites supported international telephone services, television broadcasting, data transmission, and corporate communication networks. Satellite systems provided connectivity for remote regions lacking terrestrial infrastructure. Improvements in transponder technology, signal compression, and ground station equipment increased satellite efficiency and broadened its applications. Governments, research institutions, and multinational corporations use satellite networks to support data exchange, remote sensing, and information distribution across global organizations. Telecommunications modernization influenced corporate operations extensively. Businesses adopted digital private branch exchange systems to manage internal communication. Local area networks connected office computers, enabling file sharing and centralized printing. Modems allowed remote employees to access corporate systems. Large corporations used leased digital lines and satellite networks to coordinate production, manage supply chains, and exchange information across geographically distributed sites. These developments increased organizational efficiency and strengthened the role of communication networks in business management. The expansion of data communication networks paralleled these changes. Packet switching networks, influenced by earlier ARPANET developments, expanded into commercial and governmental sectors. In the United States, the National Science Foundation created InfNet, a high-speed network supporting university research. In Europe, academic and government networks provided communication links across institutions. X25-based public data networks operated in many countries, allowing businesses to transmit information between remote offices. These networks, while limited by later standards, represented important steps toward widespread digital connectivity. Telecommunications policies changed during the 1980s as governments restructured regulatory systems. The United States underwent major deregulation following the breakup of the Bell system in 1984. This restructuring ended AT&T's monopoly over long-distance services and allowed new companies to enter the market. Deregulation increased competition, reduced prices, and accelerated infrastructure modernization. Other countries pursued varying degrees of deregulation, privatization, or restructuring to support technological upgrades and encourage investment. These policy changes reflected recognition that modern telecommunications required flexible, innovation-driven market structures. International standards played an important role in telecommunications development. Organizations such as the International Telecommunication Union and the International Organization for Standardization coordinated technical standards for digital switching, communication protocols, and fiber optic systems. The adoption of common standards facilitated equipment interoperability, international connectivity, and global communication services. Key standards included digital signaling systems, error correction methods, and interface protocols for public data networks. These technical frameworks supported reliable communication across national boundaries. Telecommunications modernization influenced industrial automation and manufacturing. Digital networks allowed factories to connect distributed control systems, enabling tighter coordination of production processes. Remote monitoring and diagnostic systems became increasingly common, allowing engineers to analyze equipment performance from centralized control rooms. Data logging improved process optimization and energy management. Automation systems incorporating microprocessors and digital communications supported just-in-time production methods and more efficient supply chain coordination. These developments increased productivity and contributed to broader industrial modernization. Mobile communication began influencing the logistics and transportation sectors. Companies used early mobile systems to coordinate vehicle fleets, monitor delivery operations, and improve scheduling. Although bandwidth limitations restricted data-intensive applications, voice communication supported operational efficiency. Early experiments with mobile data terminals appeared in emergency services, taxi fleets, and delivery systems. These developments demonstrated the potential of mobile communication for real-time operational coordination, a capability that would expand dramatically in subsequent decades. Computer communication evolved in office environments as networking technologies expanded. Ethernet became increasingly common, offering higher speeds and greater reliability than earlier interfaces. Token ring networks, promoted by IBM, provided an alternative architecture used in corporate environments. Networked workstations allowed teams to collaborate more effectively and share information across departments. File servers, print servers, and database systems supported centralized information management. These developments formed the basis for client-server computing models that became prominent in the 1990s. The consumer market began adopting digital communication technologies as costs declined. Residential telephone services improved through digital switching. Early home computers used modems to connect to bulletin board systems and online information services. Fax machines, enabled by digital communication protocols, became common in business and home environments. Video game consoles, although not directly connected to telecommunications networks at this stage, benefited from improved semiconductor and communication technologies that supported more complex systems. Telecommunications modernization affected scientific research significantly. High-speed data transfer supported collaboration among research institutions, enabling shared access to databases, computing resources, and measurement instruments. Remote sensing data from satellites supported environmental monitoring, weather forecasting, and geoscience research. Distributed computing experiments explored methods for linking supercomputers and specialized instruments across networks. These developments expanded research capabilities and supported the growth of data-intensive scientific fields. International communication increased dramatically as telecommunications infrastructure expanded. Businesses, governments, and individuals benefited from lower communication costs, higher reliability, and wider service availability. International telephone services improved in quality and affordability. Satellite links supported global broadcasting and information dissemination. Fiber optic cables began serving transoceanic communication routes, increasing capacity and reducing latency. These developments contributed to greater global economic integration and facilitated the expansion of international trade and financial networks. Telecommunications modernization influenced geopolitical relationships. Countries that invested heavily in digital infrastructure gained strategic advantages in economic competitiveness, information management, and technological innovation. Nations with limited telecommunications resources faced challenges in participating fully in emerging digital economies. International collaboration and investment projects sought to improve connectivity across different regions. The availability of reliable communication networks became a central factor in national development strategies. By the end of the 1980s, telecommunications and mobile networks had become essential components of global technological infrastructure. Fiber optics supported high-capacity communication links across countries and continents. Digital switching systems replaced older analog equipment, increasing network efficiency and enabling advanced services. Satellite networks provided global coverage. Mobile telephony expanded from early analog systems to growing subscriber bases in industrialized countries. Data networks connected research institutions, businesses, and government agencies. Regulatory changes encouraged competition and investment. International standards ensured interoperability across equipment and networks. The developments of the 1980s represent a major turning point in the Third Industrial Revolution. Telecommunications modernization enabled digital communication on a scale not previously possible. The emergence of mobile networks introduced new forms of connectivity. Data communication expanded beyond research institutions into commercial environments. These changes supported the continued growth of computing, automation, and global economic integration. The communication infrastructure established during this decade formed the basis for the rapid expansion of the Internet, mobile data networks, and digital services that followed in the 1990s and 2000s. Telecommunications and mobile networks, therefore, occupy a central place in the history of digital transformation. By establishing high-speed, reliable communication systems. The developments of the 1980s created the conditions for global digital connectivity. These systems supported industrial modernization, facilitated scientific collaboration, and reshaped economic structures. The transition from analog to digital communication, combined with the rise of mobile telephony and data networks, defined a major phase of the Third Industrial Revolution. The 1980s marked a major transformation in global financial systems as digital technologies reshaped banking operations, capital markets, and international economic integration. During this decade, electronic trading platforms, automated teller machines, digital settlement systems, and global communication networks altered how financial institutions processed transactions, assessed risk, and managed capital. These developments advanced the Third Industrial Revolution by applying digital systems to financial infrastructure, enabling faster, more reliable, and more interconnected global markets. The shift from manual and analog processes to digital systems changed the structure of banking, supported new financial products, and increased the speed of global economic activity. Automated teller machines expanded rapidly during the 1980s, transforming retail banking access. ATMs had appeared in earlier decades, but widespread adoption occurred during this period due to improvements in reliability, security, and communication networks. Banks deployed thousands of machines across urban and suburban areas, allowing customers to withdraw cash, check account balances, and perform basic transactions outside traditional banking hours. The expansion of ATM networks required secure digital communication systems to verify account information and manage transactions in real time. Shared ATM networks formed as banks cooperated to expand coverage. These networks, supported by interbank settlement systems, represented early examples of large-scale digital financial infrastructure. Electronic funds transfer systems have developed significantly. Banks used automated clearing houses to process recurring payments, such as payroll deposits and bill payments. These systems group transactions into batches and process them electronically, reducing reliance on paper checks and manual sorting. Electronic funds transfer at the point of sale also expanded as retailers adopted payment terminals capable of verifying card transactions through digital networks. These technologies increased transaction speed and improved security through encryption and digital authentication methods. The Society for Worldwide Interbank Financial Telecommunication expanded its role in international finance during the 1980s. SWIFT provided a standardized messaging system that allowed banks and financial institutions to exchange payment instructions, securities settlement messages, and trade documentation securely. The SWIFT network increased transaction reliability and reduced errors by replacing telex-based communication. By the late 1980s, thousands of institutions across dozens of countries used SWIFT for cross-border financial operations. The network became a central component of global finance, supporting the rapid growth of international trade and investment. Electronic trading platforms emerged as major developments in financial markets. Stock exchanges in the United States, Western Europe, and Japan introduced digital systems to support order entry, matching, and settlement. The NASDAQ system, launched in the early 1970s, evolved during the 1980s into a fully electronic quotation and trading platform. It provided real-time price information and facilitated transactions between dispersed market participants. Other exchanges introduced similar technologies. Digital platforms increased transparency, reduced the need for physical trading floors, and enabled algorithmic and high-volume trading strategies. These developments represented a fundamental shift from manual floor-based trading to electronic markets. Financial institutions adopted digital risk management tools during this decade. Advances in computing allowed banks to model market fluctuations, assess credit risk, and manage portfolios using statistical and computational methods. Value-at-risk models, though not yet widespread, began emerging conceptually through research in financial mathematics. Digital systems supported real-time monitoring of market positions and exposures. These capabilities increased financial institutions' capacity to manage complex operations and facilitated the development of new financial instruments. International capital flows increased substantially due to improved communication infrastructure. As telecommunications networks modernized and global data links expanded, financial institutions coordinated operations across continents with reduced delays. Foreign exchange markets became more active due to electronic trading and improved information distribution. Cross-border investment increased as digital systems enabled rapid settlement and reduced operational barriers. These developments contributed to financial globalization and increased interdependence among national economies. The expansion of digital finance influenced corporate operations. Companies managed cash flows, payroll systems, procurement, and sales processes using digital accounting software and enterprise systems. Corporate treasury operations used electronic systems to manage liquidity and coordinate international transactions. Multinational corporations relied on digital financial communication to move capital between subsidiaries, manage currency exposure, and allocate resources efficiently. These changes strengthened the integration between corporate management and digital financial systems. Government institutions adopted digital systems for taxation, budgeting, social security payments, and debt management. Central banks used digital tools to monitor economic indicators, manage monetary policy operations, and coordinate with financial institutions. Digital communications supported the distribution of policy information and market data, improving transparency and operational efficiency. These developments increased the role of digital infrastructure in national economic management. Stock exchanges outside the United States have also modernized. The London Stock Exchange began implementing its digital Big Bang reforms, culminating in the elimination of fixed trading commissions in 1986 and the transition to electronic trading systems. These reforms increased competition and facilitated the entry of international financial institutions. Japan's financial markets expanded significantly, driven by economic growth, rising asset values, and advanced telecommunications infrastructure. The Tokyo Stock Exchange increased digital capabilities and benefited from Japan's strong semiconductor and computer industries. European stock exchanges in Frankfurt, Paris, and Milan modernized trading and settlement systems, adopting electronic technologies to improve efficiency and transparency. Clearing and settlement systems underwent major upgrades. Securities depositories implemented digital record-keeping to track ownership, reducing reliance on paper certificates. Electronic settlement reduced processing time and minimized operational risk. Central securities depositories and clearinghouses used digital systems to coordinate the transfer of securities and funds between market participants. These systems supported increased trading volumes and reduced the likelihood of settlement failures. Digital clearing and settlement represented a foundational enhancement that supported global market expansion. Payment card networks expanded significantly. Credit card companies improved digital authorization, fraud detection, and settlement systems. Electronic verification reduced transaction times and increased security. Debit card adoption expanded as ATM networks integrated with point-of-sale systems. Retailers implemented electronic payment terminals that communicated with financial institutions over secure digital networks. These developments signaled a broader shift toward electronic payment systems and reduced dependence on cash. The 1980s also saw the early development of electronic financial databases and information services. Companies such as Bloomberg and Reuters provided real-time market data, financial news, and analytics to traders, analysts, and institutions. Digital terminals allowed subscribers to access up-to-date information essential for financial decision-making. These systems integrated telecommunications, computing, and financial data processing, supporting rapid analysis of market conditions. Access to real-time information increased market efficiency and influenced trading strategies. Financial integration influenced economic globalization. Countries liberalized capital accounts, allowing greater movement of funds across borders. International banks expanded operations into new markets, supported by digital infrastructure capable of coordinating global activities. Financial centers in New York, London, Tokyo, Frankfurt, and Hong Kong strengthened their positions through advanced digital systems. These centers became nodes in a global network of capital flows, supported by telecommunications, electronic trading systems, and cross-border financial institutions. Regulatory frameworks evolved to address the growing complexity of digital finance. Governments implemented regulations governing electronic trading, settlement systems, and financial communication. Central banks developed oversight mechanisms for digital payment systems to ensure stability and security. International organizations, including the Bank for International Settlements, studied systemic risk and cross-border financial linkages. These developments reflected recognition that digital financial systems required robust oversight to manage operational and market risks. Digital finance influenced labor markets within the financial sector. Institutions require personnel skilled in computing, programming, and systems management. Financial analysts use digital tools to evaluate market data, increasing demand for quantitative expertise. Software developers created applications for trading, risk management, and financial modeling. These shifts altered the composition of the financial workforce and demonstrated the increasing role of technical skills in financial operations. Emerging economic challenges appeared as financial markets expanded. Increased market volatility, driven in part by rapid information flow and electronic trading, contributed to events such as the 1987 stock market crash. Although the crash had multiple causes, the role of computerized trading and rapid market reactions demonstrated the interconnectedness introduced by digital finance. The event led to increased scrutiny of market structures, trading algorithms, and the interaction between human decision-making and electronic systems. It also influenced regulatory considerations for managing digital markets. Despite challenges, the decade's developments established digital finance as a permanent component of global economic systems. Electronic markets became standard in major exchanges. Digital communication networks supported global capital mobility. Banking operations incorporated automated systems for transactions, record-keeping, and customer service. Payment systems expanded beyond cash and checks to include electronic methods. These changes increased efficiency, supported economic growth, and enabled the emergence of new financial products and services. By the end of the 1980s, digital technologies had reshaped global finance. Transactions flowed across borders through digital communication networks. Markets operated electronically, supported by real-time data and high-capacity systems. Banks and financial institutions relied on digital infrastructure for daily operations. Governments used electronic systems for fiscal and monetary management. The integration of digital technologies into finance supported the broader expansion of global economic activity and contributed to the increasing complexity of international markets. The developments of the 1980s represent a significant phase in the Third Industrial Revolution. Digital finance accelerated the speed and scale of global markets, increased the interconnectedness of national economies, and reinforced the role of information technology in economic activity. Electronic trading, automated banking systems, and global financial networks laid the foundation for modern digital finance and influenced economic patterns for decades. The integration of digital technologies into financial infrastructure marked a major structural shift in global economic systems. Digital finance, therefore, occupies a central position in the history of global integration. By linking communication technology, computing, and financial operations, the developments of the 1980s created a new economic environment characterized by rapid information flow, interconnected markets, and enhanced institutional capabilities. These changes contributed to the continued expansion of the digital economy and shaped the financial landscape of the late 20th and early 21st centuries. The years from 1990 to 1995 represent the transition from specialized research networks to a global, publicly accessible digital communication system. During this period, the modern internet emerged through the consolidation of networking protocols, the development of user-oriented tools, the expansion of commercial service providers, and the establishment of foundational infrastructure. These developments transformed networked communication from a domain of research institutions and government agencies into a rapidly expanding global system accessible to businesses, educational institutions, and the general public. The period marks the beginning of large-scale digital communication as a central component of economic, social, and institutional activity. A major development occurred in 1990 when the original ARPANET was formally decommissioned. By this time, the network's role had shifted as newer systems and updated protocols expanded beyond ARPANET's original architecture. The decommissioning marked the end of the first operational packet switching network and symbolized the transition to a new generation of communication technologies. The foundational principles developed through ARPANET, packet switching, host-to-host protocols, and distributed network architecture remained central to subsequent systems. But the infrastructure supporting global networking expanded far beyond its initial scope. In 1983, the transition from the Network Control Protocol to the Transmission Control Protocol and Internet Protocol established a unified communication standard for interconnected networks. By the early 1990s, TCP/IP served as the primary protocol suite for academic, governmental, and increasingly commercial networks. The uniformity of TCP/IP facilitated interoperability, enabling diverse systems and organizations to connect without requiring specialized coordination. This standardization created conditions for rapid growth as computer networks adopted compatible protocols across national boundaries. The National Science Foundation Network played a central role in expanding the Internet during this period. INSFnet functioned as a high-speed backbone connecting research institutions across the United States. Throughout the late 1980s and early 1990s, NSF upgraded the network's capacity, supporting transmission speeds that increased from 56 kilobits per second to T1 and later T3 lines. INSFnet interconnected universities, laboratories, and regional networks, providing large-scale support for data exchange, scientific collaboration, and distributed computing. The network structure demonstrated the feasibility of high-capacity public research networks and influenced global network development. International networking expanded in parallel. European research networks, including ERN and EBONY, established connections across national research institutions. The United Kingdom's JANET network, Germany's DFN, and other European systems adopted TCP/IP, improving compatibility with global networks. In Japan, the WIDE project and related initiatives connected research institutions and supported experimental networking technologies. These developments produced a growing international infrastructure based on common technical standards and supported by academic, governmental, and commercial organizations. The invention of the World Wide Web in 1989 by Tim Berners-Lee at CERN represented a major turning point in network usability. By developing the Hypertext Transfer Protocol, the Hypertext Markup Language, and the concept of the Uniform Resource Locator, Berners-Lee introduced a system capable of linking documents across networks seamlessly. Early versions of the web provided text-based navigation and allowed researchers to share information through interconnected documents. The web offered a conceptual framework that simplified information retrieval and provided a platform for expanding content and applications. In 1993, the release of the Mosaic web browser accelerated public adoption of the Internet. Developed at the National Center for Supercomputing Applications at the University of Illinois, Mosaic provided a graphical interface that supported images, user-friendly navigation, and cross-platform compatibility. Its design made the web accessible to users without specialized technical knowledge. Mosaic's popularity contributed to rapid growth in websites, online content, and commercial interest in digital information distribution. The browser demonstrated that graphical interfaces could significantly expand the usability and appeal of networked communication. Commercial internet service providers expanded rapidly between 1992 and 1995. As INSFnet gradually transitioned towards supporting research functions rather than commercial traffic, private companies began offering dial-up access to individuals and businesses. ISPs such as UUNet, PSINet, Netcom, and America Online facilitated public access to the Internet through telephone networks. Subscription-based access allowed users to browse the web, use electronic mail, and participate in early forms of online interaction. The expansion of ISPs supported the transition from a specialized research network to a global communication system with millions of users. Electronic mail became one of the most widely used Internet applications during this period. Email systems expanded beyond research institutions into corporate, governmental, and personal communication. Standardized protocols such as SMTP, POP, and IMAP enabled reliable transmission and retrieval of messages. Businesses adopted email for internal coordination, external communication, and document distribution. The widespread use of email demonstrated the practical value of the Internet for rapid information exchange. The early 1990s also witnessed growth in file transfer, discussion forums, and online distribution of software and documents. File transfer protocol servers provided access to software archives, academic papers, and technical materials. Usenet forums allowed global discussion across thousands of topic areas. These systems demonstrated the Internet's capacity for information sharing and collective exchange before the web became dominant. Although text-based interactions remained prevalent, the web rapidly gained momentum due to its graphical capabilities and ease of navigation. Domain name system expansion supported the growth of the Internet by providing structured addressing for an increasing number of sites. The DNS, introduced in the mid-1980s, assigned hierarchical domain names to organizations, countries, and individuals. By the early 1990s, new top-level domains, registration authorities, and administrative procedures expanded DNS capacity. This system allowed users to access sites using human-readable names rather than numerical IP addresses, improving usability and supporting large-scale network growth. Telecommunications infrastructure upgrades contributed significantly to Internet expansion. Fiber optic networks improved transmission capacity, and digital switching systems supported increased data traffic. Telephone carriers introduced integrated services, digital network technologies that enabled higher-speed data transmission for early Internet users. International communication links expanded through undersea fiber optic cables, supporting faster and more reliable global connectivity. These upgrades allowed the Internet to handle increasing traffic volumes and supported the growth of commercial and educational use. Governments and institutions recognized the Internet's strategic importance. Policies began addressing network governance, resource allocation, and long-term infrastructure development. In the United States, responsibility for coordinated management of domain names and IP address allocation involved NSF and related organizations. Other countries developed national Internet governance structures. International collaboration grew through organizations addressing technical standards, infrastructure coordination, and academic networking. These developments provided administrative frameworks that supported the Internet's transition into a global communication system. Businesses began adopting Internet technologies for marketing, communication, and information distribution. Early corporate websites provided product information, technical support materials, and company profiles. Although electronic commerce remained limited during this period, foundational systems such as secure communication protocols and payment standards began emerging. The commercial potential of the Internet became increasingly apparent as user numbers grew and private companies recognized the value of online presence. Educational institutions expanded Internet access to support coursework, research collaboration, and information retrieval. Libraries connected to the Internet, providing access to catalogs, databases, and reference materials. Universities integrated network communication into curricula in computer science, engineering, and information studies. These developments increased digital literacy and supported broader integration of network technologies into academic environments. By the mid-1990s, the Internet had become a rapidly expanding global system. User populations grew from hundreds of thousands in the late 1980s to tens of millions by 1995. The number of websites increased exponentially following the introduction of graphical browsers. Commercial activity expanded, though still in early stages. Governments recognized the Internet's importance for communication, research, and economic development. Telecommunications infrastructure continued to be upgraded to support rising traffic. The developments from 1990 to 1995 represent a foundational phase in the history of global digital communication. The decommissioning of ARPANET marked the conclusion of the earliest era of packet switching networks. The standardization of TCP/IP provided universal interoperability. InfNet demonstrated the feasibility of high-speed research backbones. The World Wide Web introduced a simple, flexible method for organizing and accessing information. Graphical browsers expanded usability and accelerated adoption. Commercial internet service providers made the internet widely accessible. Email, file transfer, and online forums demonstrated practical applications of network communication. Telecommunications upgrades supported increased data traffic and global connectivity. These developments transformed the internet from a specialized research tool into a public communication system. The combination of technical innovation, institutional support, and commercial expansion created the conditions for the rapid growth that followed in the late 1990s and early 2000s. The period established the core structures of the internet as a global network: standardized protocols, distributed governance, interoperable infrastructure, and user-oriented tools. The early internet era, therefore, represents a major turning point in the third industrial revolution. By making digital communication widely accessible and usable, the developments from 1990 to 1995 set the foundation for the interconnected global society that emerged in subsequent decades. The internet became a central platform for information exchange, economic activity, scientific collaboration, and social interaction, defining the next phase of digital transformation. The 1990s represent a significant restructuring of global manufacturing and logistics as digital technologies integrated with transportation, communication, and production systems. During this decade, supply chains became increasingly international, driven by advances in containerized shipping, real-time data exchange, and the rise of newly industrializing economies. Modern logistics networks emerged, characterized by coordinated production across multiple countries and supported by digital planning tools, enterprise management systems, and improved transportation infrastructure. These developments fundamentally altered global economic structures and formed a major component of the Third Industrial Revolution. Containerization had achieved widespread adoption by the early 1990s and became the backbone of global trade. Standardized containers, modular handling equipment, and automated port infrastructure transformed international shipping by reducing loading times, minimizing cargo damage, and supporting predictable scheduling. By the beginning of the decade, major ports in the United States, Western Europe, and East Asia operated large container terminals capable of handling millions of 20-foot equivalent units annually. Automated gantry cranes, computerized yard management systems, and coordinated rail and trucking networks allowed rapid movement of goods from ships to inland destinations. These developments supported high-volume trade and facilitated the global distribution of manufactured goods. Digital technologies have enhanced logistics operations significantly. Companies adopted enterprise resource planning systems that integrated procurement, inventory management, production scheduling, and distribution into unified digital environments. ERP systems provided real-time visibility into supply chain operations, and allowed organizations to coordinate production across multiple facilities and countries. Manufacturing resource planning tools supported material requirements planning, capacity allocation, and workflow optimization. These systems reduced waste, improved scheduling accuracy, and supported just-in-time production strategies. Globalization accelerated as transportation costs declined and digital coordination improved. Firms distributed production stages across countries to take advantage of varying labor costs, industrial capabilities, and regulatory environments. Components were manufactured in multiple locations before final assembly in centralized facilities. Digital communication systems, including email, EDI platforms, and early commercial internet tools, enabled rapid exchange of technical specifications, procurement data, and production schedules. These new forms of coordination allowed firms to operate complex supply chains with reduced delays and increased flexibility. Newly industrializing economies became central components of global production networks. South Korea, Taiwan, Singapore, and Hong Kong, often referred to as the Four Tigers, expanded their industrial capacities significantly. South Korea developed advanced electronics, automotive components, and shipbuilding industries. Conglomerates invested in research, manufacturing, and global distribution systems. Taiwan became a major producer of semiconductors, computer components, and consumer electronics, supported by strong engineering education and government-led industrial policy. Singapore built advanced manufacturing facilities, logistics hubs, and semiconductor fabrication plants. Hong Kong served as a financial and commercial center supporting trade across East Asia. Southeast Asian nations, including Malaysia, Thailand, and Indonesia, expanded manufacturing of electronics, appliances, and machinery components. These countries leveraged competitive labor markets and improved infrastructure to attract foreign direct investment. Industrial parks, export processing zones, and government incentives supported growth. The integration of Southeast Asian production into global supply chains increased regional economic importance and diversified global manufacturing capacity. China's economic reforms accelerated global restructuring dramatically. Following earlier phases of market liberalization, China established special economic zones, encouraged foreign investment, and expanded export-oriented manufacturing. By the mid-1990s, China had become a major source of consumer electronics, textiles, machinery components, and household appliances. Infrastructure improvements, including port modernization and expanded transportation networks, supported large-scale manufacturing expansion. Digital technologies allowed coordination between Chinese production facilities and global corporations, facilitating integration into international supply chains. Logistics companies expanded operations to support global trade. Firms such as DHL, FedEx, UPS, and major national postal services developed international networks supporting express delivery, cargo transportation, and supply chain management services. These companies adopted digital tracking systems that provided real-time shipment information. Barcoding, introduced earlier, became standard across transportation networks, enabling automated sorting and improved accuracy. These capabilities supported reliable delivery schedules and enhanced global business operations. Retail and consumer product companies transformed sourcing strategies. Organizations such as Walmart, Carrefour, and other large retailers developed global procurement systems enabled by digital communication and enterprise planning tools. These companies coordinated suppliers across multiple continents, optimizing cost, quality, and delivery schedules. Digital inventory systems allowed real-time monitoring of stock levels, enabling efficient replenishment. The combination of large-scale retail networks and global sourcing reshaped consumer markets and increased the influence of multinational corporations on manufacturing patterns. The expansion of global supply chains influenced industrial production structures. Factory specialization increased as firms concentrated on specific stages of production where they held cost or technological advantages. Contract manufacturing emerged as a major industry, with companies producing components or final products for multiple global brands. Electronics manufacturing services firms in Taiwan, China, and Southeast Asia produce computer hardware, mobile phones, and consumer devices for international companies. This specialization demonstrated the shift from vertically integrated production structures to distributed, collaborative networks. Regulatory environments influenced globalization patterns. Trade agreements, such as the North American Free Trade Agreement, the formation of the European Single Market, and the expansion of the World Trade Organization facilitated the cross-border movement of goods and investment. These agreements reduced tariffs, standardized regulations, and supported global market integration. Countries with favorable trade policies attracted manufacturing investment and became key nodes in global supply chains. Information technology advanced rapidly during this period, supporting real-time coordination of production and distribution. Companies used digital forecasting tools to predict demand, adjust production levels, and manage inventory. Telecommunications networks enabled the rapid exchange of communications across continents. Electronic data interchange became standard for transmitting invoices, purchase orders, and shipping documents between companies and suppliers. These systems reduced administrative delays and increased the speed of business operations. Transportation networks improved in capability and efficiency. Maritime shipping companies expanded fleets with larger container vessels capable of carrying thousands of containers per voyage. Ports installed automated cranes and computerized management systems to support rapid loading and unloading. Air cargo networks grew as companies used air transport for high-value or time-sensitive goods. Improved road and rail infrastructure facilitated the inland transportation of goods from ports to regional distribution centers. These developments increased global trade capacity and reduced transit times. The growth of global supply chains influenced labor markets and economic development patterns. Newly industrializing economies experienced rapid employment growth in manufacturing sectors, contributing to rising incomes and expanding middle classes. Industrialized nations experienced shifts in employment patterns as production moved offshore, increasing demand for skilled labor in design, engineering, logistics, and information management. These changes reflected global economic restructuring driven by technological and logistical factors. Environmental and resource management considerations also emerged during this period. Increased production and transportation volumes raised concerns about energy consumption, emissions, and environmental sustainability. International organizations and national governments began assessing the environmental impacts of global supply chains. These considerations influenced early discussions about sustainable production and resource-efficient manufacturing. Although environmental regulations varied widely by country, the issue became increasingly prominent within global economic policy. Financial integration supported global supply chains by providing accessible investment, credit, and risk management tools. Banks and financial institutions offered trade financing, currency exchange services, and investment capital. Digital financial systems, introduced in earlier stages of the Third Industrial Revolution, supported the rapid settlement of international transactions. These financial capabilities reduced operational barriers for companies conducting business across multiple regions. Global supply chain risks also became more apparent. The complexity of distributed production networks exposed companies to disruptions caused by strikes, natural disasters, political instability, or logistical delays. These challenges influenced the development of risk management strategies, including supplier diversification, inventory buffering, and improved monitoring systems. Digital tools supported these efforts by providing real-time information about production schedules, transportation networks, and market conditions. By the late 1990s, global supply chains had become highly integrated, digitally managed systems. Containerization supported the large-scale movement of goods across continents. ERP systems coordinated production and distribution. Newly industrializing economies produced a significant share of global manufactured goods. Telecommunications networks provided real-time communication across geographically distributed operations. Retailers and manufacturers used digital systems to manage complex procurement and inventory processes. These developments reshaped global economic structures and increased the interdependence of national economies. The restructuring of global production and logistics during the 1990s represents a major phase of the Third Industrial Revolution. Digital coordination enabled international supply chains operating on an unprecedented scale. Manufacturing spread across multiple regions, supported by specialized industrial capacities and improved infrastructure. Retail and corporate procurement strategies expanded global demand for manufactured goods. Transportation and communication technologies supported rapid, reliable distribution. These changes influenced global trade patterns, industrial development, and economic relationships among nations. The integration of digital systems with global logistics, therefore, occupies a critical position in the history of the Third Industrial Revolution. The developments of the 1990s established the foundation for the even more complex supply chain networks that emerged in subsequent decades. By combining information technology, transportation infrastructure, and international industrial capacity, the global economy became more interconnected, efficient, and dependent on coordinated digital systems. The late 1990s represent a period of accelerated integration of digital technologies into industrial, commercial, and administrative systems. During this phase, enterprise computing expanded across global corporations. Second-generation industrial robots gained higher capabilities, and automated logistics became essential to supply chain operations. The combined influence of improved software, expanded telecommunications infrastructure, and advanced manufacturing equipment reshaped organizational structures and increased productivity. By the end of the decade, automation had become a central feature of global economic activity, supporting the consolidation of digital processes across white-collar and blue-collar sectors. Enterprise computing expanded significantly during this period as companies adopted integrated digital systems to manage operational functions. Enterprise resource planning software linked procurement, accounting, inventory, human resources, and production into unified platforms. These systems replaced fragmented departmental tools with standardized databases and centralized oversight mechanisms. Major corporations adopted ERP systems to coordinate activities across geographically distributed facilities. Implementation required redesigning workflows, updating data structures, and training staff to operate new systems. Although deployment was complex and resource-intensive, ERP systems provided improved data accuracy, increased operational transparency, and enhanced coordination across supply chain networks. Manufacturing environments adopted computer-integrated manufacturing systems as digital control became standard. CIM systems combined production planning, machine control, robotics, and automated inspection into interconnected structures. These systems leveraged sensors, industrial networks, and real-time processing to monitor production status, adjust workflow, and coordinate equipment with minimal operator intervention. Manufacturing execution systems tracked work orders, inventory movement, and equipment utilization. These tools supported lean production practices and increased throughput. Second-generation industrial robots became more capable during the late 1990s. Robots used improved servo motors, advanced control algorithms, and increased computational power. These capabilities provided higher precision, greater repeatability, and faster response times. Robots gained expanded functionality through multi-axis articulation and integration with machine vision systems. Vision-guided robots perform tasks requiring alignment, object recognition, and inspection. Force feedback systems allowed robots to adjust movements when encountering variable materials or assembly tolerances. These improvements expanded robotic applications into electronics manufacturing, pharmaceuticals, packaging, and advanced automotive assembly. Japan continued leading global robot deployment, with thousands of new installations annually. Japanese companies used robots extensively in welding, painting, assembly, and inspection. Factories implemented flexible manufacturing systems capable of rapid reconfiguration for new product lines. Automotive manufacturers integrated robots into nearly every stage of production, achieving high consistency and reduced defect rates. Europe also expanded robotic adoption, particularly in Germany and Italy, where robotics supported precision engineering and automotive production. The United States increased robot deployment in the aerospace, electronics, and automotive sectors, supported by improvements in domestic machine vision research and industrial automation systems. Automation expanded beyond manufacturing into logistics and distribution. Warehouses implemented automated storage and retrieval systems supported by computer-controlled cranes, conveyors, and sorting equipment. Barcode scanning and later radio frequency identification systems improved inventory tracking. Warehouse management software optimizes storage allocation, picking routes, and replenishment schedules. Distribution centers are connected to suppliers and retailers through enterprise systems, enabling real-time coordination of shipments. These developments improved throughput, reduced labor requirements, and supported the high-volume movement of goods characteristic of late 1990s global supply chains. The expansion of e-commerce during the late 1990s increased demand for automated logistics. Companies built distribution centers optimized for rapid order fulfillment. Automated conveyor systems supported high-speed sorting of individual items. Digital coordination between retail platforms and warehouses allowed near real-time updates of inventory status. Although early e-commerce volumes remained modest relative to later decades, the infrastructure established during this period demonstrated the feasibility of large-scale digital retail supported by automated logistics systems. Telecommunications networks continued expanding, providing a foundation for enterprise automation. Fiber optic systems supported high-capacity data transmission between corporate sites. Wide area networks connected regional offices, production facilities, and data centers. Internet connectivity enabled remote access to corporate resources and supported early web-based applications. These communication systems facilitated distributed operations across multiple regions and accelerated the international integration of corporate activities. The Internet's growing commercial presence influenced automation strategies. Companies used web-based systems for procurement, supply chain coordination, and information exchange. Early electronic marketplaces allowed businesses to buy and sell components digitally, improving access to global suppliers. Web interfaces connected customers to order tracking systems, customer support tools, and product documentation. These developments expanded the role of digital systems in business operations and increased the importance of reliable automated infrastructure. Data analysis capabilities improved as computing power increased. Corporations collected large volumes of operational data from production lines, supply chains, and financial systems. Data warehousing systems consolidate information from diverse sources, enabling analytical processing and performance monitoring. Business intelligence tools supported trend analysis, forecasting, and resource planning. These developments contributed to data-driven decision-making and increased operational efficiency. Automation influenced administrative and professional work significantly. Document processing, record-keeping, and communication shifted to digital formats. Email became the primary method for internal and external correspondence. Office productivity software supported document creation, numerical analysis, and presentation development. Networked systems allowed employees to share files, access centralized databases, and collaborate across departments. These changes altered workplace structures and increased reliance on digital tools. Customer service operations adopted automated systems. Call centers used computer telephony integration technologies to manage incoming calls, route inquiries, and provide customer information. Interactive voice response systems automated routine inquiries, reducing staffing requirements. Early web-based support systems provided documentation, troubleshooting tools, and communication channels. These developments demonstrated how automation extended beyond manufacturing into service sectors. In finance and accounting, automation increases accuracy and efficiency. Digital ledger systems managed transactions, reconciled accounts, and generated financial reports. Automated auditing tools analyzed data for inconsistencies and supported compliance. Electronic payment systems processed transactions rapidly, reducing reliance on manual procedures. These developments reflected the broader adoption of digital tools in administrative operations. Industrial robotics expanded into small and medium-sized enterprises during this period. Lower-cost robotic arms provided automation capabilities for tasks such as packaging, material handling, and small-scale assembly. Modular robotics systems enabled flexible deployment in varied environments. These developments broadened the industrial base using automation and increased accessibility for companies lacking large capital resources. Safety systems for robots and automated equipment have improved significantly. standards organizations developed guidelines for robot integration, guarding, and emergency procedures. Light curtains, safety interlocks, and controlled stop mechanisms reduced risk. Certification practices ensured machines met operational safety requirements. These advances supported wider deployment by reducing hazards associated with automated equipment. Automation in process industries continued to expand. Oil refineries, chemical plants, and power stations implemented distributed control systems using microprocessors and digital communication. These systems provided centralized monitoring of temperature, pressure, flow rates, and chemical composition. Automation improved safety, reduced waste, and ensured precise control of complex industrial processes. Real-time monitoring allowed engineers to respond quickly to deviations and maintain operational stability. Semiconductor advancements enabled deeper automation across industries. Microprocessors gained increased clock speeds, larger cache sizes, and more efficient architectures. Memory costs continued to decline, supporting the deployment of embedded systems in machinery, vehicles, and consumer devices. Programmable logic controllers gained improved performance and networking capabilities. These semiconductor improvements supported the increasing complexity of automated systems. The expansion of automation influenced labor markets. Skilled technical workers were needed to program, maintain, and repair automated equipment. Training programs expanded in vocational schools and universities. Workers transitioned from manual tasks to supervisory, technical, and analytical roles. Some industries experienced restructuring as automation replaced repetitive or physically demanding work. These shifts reflected the broader transformation of labor during the Third Industrial Revolution. Global differences in automation adoption became more pronounced. Japan and Germany maintained high levels of industrial automation, supported by advanced manufacturing sectors and strong engineering capabilities. The United States remained a leader in software, semiconductor design, and research, providing key components for global automation systems. Newly industrializing economies adopted automation selectively, focusing on sectors requiring high precision or consistency. These variations shaped global production patterns and influenced competitive dynamics. By the end of the 1990s, enterprise computing and automation systems had become integral to global business operations. ERP systems coordinated activities across large corporations. Manufacturing relied on CIM, MES, and advanced robotics. Logistics networks used automated systems and digital tracking. Telecommunications infrastructure supported distributed enterprise operations. Data analysis tools informed business decisions. Automation had expanded across manufacturing, logistics, administration, finance, and customer service. The integration of robotics, digital control, enterprise software, and logistics automation during the late 1990s represents a significant phase of the Third Industrial Revolution. These technologies deepened automation beyond localized factory operations and embedded digital systems into the core structure of global economic activity. The developments established the technological and organizational foundations for further expansion of automation, advanced robotics, and digital enterprise systems in the decades that followed. Automation during this period, therefore, occupies a critical position in modern industrial history. The capabilities developed in the late 1990s shaped manufacturing processes, corporate strategies, and global supply chain networks. These changes reinforced the role of digital technology as a central factor in economic activity and marked a major step in the evolution of integrated industrial systems. The period from 2000 to 2005 represents a major transition in global digital infrastructure as broadband networks expanded, mobile communication systems became widespread, and early Web 2.0 platforms emerged. These years mark the point at which digital connectivity reached mainstream scale in many industrialized nations and became increasingly accessible in developing regions. The combination of high-speed internet, advanced mobile networks, and widespread digital devices reshaped communication, commerce, and institutional operations. By 2005, digital connectivity had evolved from a specialized resource into a foundational component of global economic and social systems. Broadband internet expanded rapidly during this period. Early internet access in the 1990s relied primarily on dial-up connections, which offered limited bandwidth and slow data transfer rates. The transition to broadband technologies, principally digital subscriber line services and cable modem systems, provided significantly higher speeds and persistent connectivity. Telecommunications companies upgraded their infrastructure to support broadband deployment across urban and suburban regions. Transmission rates increased from kilobits to megabits per second, enabling multimedia content, large file transfers, and more complex web applications. By the mid-2000s, broadband had become the primary method of household internet access in many industrialized countries. Cable broadband services expanded through upgrades to hybrid fiber coaxial networks. Cable operators used digital modulation techniques to support high downstream speeds and stable connections. These systems provided competitive alternatives to telephone-based broadband, accelerating diffusion. Telecommunications firms deployed DSL systems over existing copper lines, providing broadband access without requiring new wiring. Improved DSL technologies increased performance by using advanced signal processing techniques. These developments enabled the rapid expansion of broadband to millions of households. Fiber optic broadband began emerging in select regions, although coverage remained limited. Fiber-to-the-home networks, deployed by some telecommunications companies in Japan, the United States, and Western Europe, demonstrated the feasibility of high-speed access delivering tens of megabits per second. Although deployment costs restricted early adoption, these systems provided a model for later large-scale fiber expansion. Broadband's increasing availability supported the development of new digital services and allowed more sophisticated applications to become practical for everyday users. Mobile communication experienced major developments during this period. Third-generation mobile networks began launching in 2001, offering improved data transmission capabilities compared to earlier systems. 3G standards supported data rates suitable for mobile internet access, multimedia messaging, and early forms of mobile software applications. Although speeds varied across networks, the shift from voice-centric to data-capable mobile systems marked a significant evolution in communication infrastructure. Mobile operators expanded coverage, upgraded switching equipment, and introduced new spectrum allocations to support increasing subscriber numbers. Mobile devices themselves have evolved. Early mobile phones gradually incorporated color displays, higher resolution screens, and expanded processing capabilities. Manufacturers introduced phones with integrated cameras, enabling digital photography and multimedia messaging. Although mobile computing remained limited compared to later smartphones, these devices demonstrated the potential for expanded mobile applications. Text messaging, already established in some regions, became widespread globally, supported by standardized protocols and low-cost communication options. Mobile communication became central to daily interactions for large segments of the global population. Wireless local area networks expanded significantly during this period. Wi-Fi technology, based on IEEE 802.11 standards, enabled high-speed wireless connectivity within homes, offices, and public spaces. Wireless access points became common in businesses and educational institutions, supporting mobile computing and flexible workspace arrangements. Laptops with integrated wireless capabilities became widespread, enabling connectivity without reliance on wired Ethernet. Wi-Fi played a major role in extending broadband access within local environments and supported new forms of digital mobility. The expansion of broadband and mobile networks influenced the development of online services and digital platforms. Early Web 2.0 applications emerged between 2003 and 2005, emphasizing user-generated content, interactive interfaces, and dynamic information exchange. Websites adopted technologies enabling real-time updates, multimedia integration, and social interaction. These platforms represented a shift from static, document-oriented sites toward interactive digital environments. Although the scale of social media remained limited in these early years, foundational systems began influencing digital communication patterns. Search engines improved significantly during this period, reflecting the growing volume of online information. Algorithms prioritized relevance, link structure, and content quality. Search services became core components of digital navigation, supporting research, commerce, and communication. These improvements demonstrated how broadband-enabled content growth required more advanced tools for information retrieval. E-commerce stabilized and expanded after earlier fluctuations. Companies improved logistics integration, online payment systems, and customer service platforms. Broadband enabled more reliable transaction processing, multimedia product displays, and electronic communication with customers. Businesses adopted online ordering systems for retail, travel services, and professional offerings. The increasing reliability of digital infrastructure supported public confidence in online commerce. Digital media distribution expanded rapidly. Audio and video content became more accessible due to increased bandwidth. Streaming media services began offering limited libraries, demonstrating potential for digital content distribution. Downloadable music platforms emerged as alternatives to physical media. Although online video remained constrained by bandwidth limitations, early platforms provided previews of future large-scale streaming services. The expansion of digital media distribution influenced entertainment industries and accelerated the shift toward online platforms. Institutions adopted broadband and digital communication extensively. Government agencies implemented online portals for public services, documentation, and communication. Educational institutions expanded digital resources, supporting online research, coursework, and distance learning. Health systems used digital platforms for record-keeping, scheduling, and communication. Scientific research benefited from improved data exchange, distributed computing capabilities, and access to global information networks. Businesses integrated broadband into operations to support communication, collaboration, and coordination. Corporate networks upgraded to support higher data traffic, video conferencing, and distributed work environments. Companies expanded intranet and extranet systems, enabling secure communication with employees, partners, and suppliers. Digital document management systems replaced physical storage, increasing efficiency. These developments strengthened the role of broadband as essential infrastructure for modern organizational operations. Global differences in broadband and mobile adoption emerged during this period. Industrialized countries saw rapid expansion, while developing regions experienced more gradual growth due to infrastructure costs and economic constraints. Mobile networks, however, expanded rapidly in many developing regions, offering communication access without requiring extensive wired infrastructure. Mobile adoption increased economic participation and supported access to information and communication services in areas previously underserved by traditional telecommunications systems. The growth of digital communication influenced economic structures. Companies expanded online marketing, digital advertising, and electronic customer service channels. Delivery companies implemented improved tracking systems supporting online order visibility. Financial institutions expanded online banking, enabling customers to access accounts, transfer funds, and manage payments remotely. Digital communication became integral to daily financial, commercial, and administrative activity. Cybersecurity became increasingly important as broadband expanded. Institutions implemented firewalls, encryption systems, and intrusion detection tools to protect networks. Cybersecurity incidents demonstrated vulnerabilities associated with widespread digital connectivity. These developments influenced long-term strategies for digital infrastructure protection. Telecommunications companies invested heavily in expanding capacity to meet rising demand. Fiber optic backbones increased in density and extended across regions. International communication routes, including undersea fiber cables, expanded significantly. These upgrades improved global internet reliability and reduced latency. Telecommunications policies are adapted to support competition, regulate broadband deployment, and encourage infrastructure investment. Mobile carriers introduced advanced services supported by 3G networks, including multimedia messaging, mobile internet browsing, and early application ecosystems. Although application distribution platforms were not yet centralized, manufacturers and operators provided software through downloadable packages and network services. These early systems demonstrated the potential for mobile devices to serve as multi-purpose digital tools. Social interaction patterns began changing due to expanded digital connectivity. Email, online forums, and emerging social platforms supported communication across distances. Broadband facilitated the use of instant messaging programs, which allowed real-time text communication. Users increasingly relied on digital communication for personal, professional, and educational purposes. By 2005, broadband and mobile networks had become central components of the global communication infrastructure. Broadband access allowed users to engage with multimedia content, use interactive applications, and participate in emerging online platforms. Mobile networks supported widespread communication and introduced data capabilities that would expand significantly in later years. Wi-Fi provided high-speed local connectivity. Digital communication influenced economic activity, institutional operations, and daily life across large portions of the global population. The developments from 2000 to 2005 represent a critical phase in the third industrial revolution. Broadband transformed the speed and scale of internet use. Mobile networks expanded digital communication beyond fixed locations. Early Web 2.0 systems introduced user-generated content and interactive platforms. Digital media began transitioning to online distribution. Businesses and institutions integrated broadband into core operations. These changes marked the moment when digital connectivity reached pervasive levels in many regions. The period, therefore, occupies a significant place in modern technological history. Broadband and mobile networks created a foundation for the digital economy, influencing how information moved, how institutions operated, and how individuals interacted. These developments set the stage for the rapid expansion of digital services, mobile computing, and large-scale online platforms in the following decade. The Third Industrial Revolution, spanning from the invention of the integrated circuit in 1958 through the consolidation of broadband and mobile networks by 2005, represents a fundamental restructuring of global technological, economic, and institutional systems. During these decades, digital technologies became embedded in nearly every aspect of production, communication, finance, logistics, and daily life. Semiconductor scaling, network expansion, automation, and information systems collectively produced a new industrial environment characterized by rapid information flow, distributed processes, and global interdependence. The legacy of this period shaped the structure of the 21st century digital economy and established technological foundations that continue to influence global development. Semiconductor technology formed the core of the Third Industrial Revolution. The invention of the integrated circuit allowed unprecedented levels of miniaturization and reliability. Throughout the following decades, advances in lithography, materials science, and semiconductor fabrication increased transistor density and reduced power consumption. Microprocessors introduced in the early 1970s transformed computer architecture, enabling compact, affordable systems. By the 1980s and 1990s, microprocessors powered personal computers, industrial equipment, telecommunications systems, and embedded devices. The expansion of semiconductor manufacturing became a global enterprise, with major production facilities in the United States, Japan, South Korea, Taiwan, and Europe. These developments established a technological platform supporting continuous innovation across all digital sectors. Computing evolved from mainframe systems serving government, research, and corporate institutions to personal computers accessible to millions of individuals. Time-sharing systems of the 1960s expanded computing access within organizations, while the emergence of personal computing in the late 1970s and early 1980s extended digital capability to households, schools, and small businesses. Graphical interfaces, standardized operating systems, and expanding software ecosystems broadened the utility of personal computers. By the mid-1980s, computing had become a central tool for administrative work, education, scientific analysis, and creative production. These developments influenced workforce skills, institutional practices, and the structure of global information exchange. Networking reshaped communication during the Third Industrial Revolution. From early packet switching experiments in the late 1960s to the establishment of global internet infrastructure by the mid-1990s, networks expanded the scale and speed of information flow. The World Wide Web introduced a standardized, accessible method for linking and sharing documents, accelerating adoption across all sectors. Graphical browsers in the 1990s transformed user interaction and made the internet a mainstream platform. The emergence of broadband networks in the early 2000s supported multimedia content, interactive applications, and large-scale digital services. Telecommunications upgrades, including fiber optic transmission, digital switching, and satellite communication, provided high-capacity infrastructure for global connectivity. These developments established the Internet as a foundational communication system for the 21st century. Automation represented another major dimension of the Third Industrial Revolution. Industrial robots, which began as simple programmable machines in the 1960s, evolved into complex, multi-axis systems capable of high-precision tasks. Numerical control and computer numerical control systems transformed machining and manufacturing. Process industries implemented distributed control systems to manage continuous operations. By the late 1990s, automation extended beyond manufacturing into logistics, retail, finance, and administrative sectors. Enterprise systems coordinated production and distribution across global networks. Automated storage, sorting, and transportation systems in warehouses enabled high-throughput logistics. These developments increased productivity, reduced errors, and supported the expansion of global supply chains. Globalization during this period reflected the combined influence of communication, transportation, and information technologies. Containerization standardized international shipping and reduced logistical costs. Digital networks allowed corporations to coordinate production across multiple countries. Newly industrializing economies expanded manufacturing capacity, supported by improved infrastructure, technical education, and investment. Supply chains became more complex and geographically distributed. These changes influenced the distribution of economic activity worldwide, contributing to rapid growth in East Asia and restructuring industrial sectors in Europe and North America. The global economic system became increasingly interconnected, with digital systems facilitating real-time coordination across continents. Finance underwent major transformations through digitalization. Electronic markets replaced manual trading systems. Automated teller machines expanded access to retail banking. Electronic payment systems and digital settlement tools increased transaction speed and reliability. Global financial networks enabled the rapid movement of capital and increased cross-border investment. These developments altered the structure of financial markets and expanded the scale of global economic integration. Digital finance supported corporate operations, international trade, and economic policymaking, becoming an essential component of modern financial systems. Institutional structures adapted to digital technologies. Governments implemented electronic systems for administration, taxation, and social services. Educational institutions integrated digital resources into teaching and research. Businesses adopted digital tools for communication, collaboration, and workflow management. These changes altered organizational processes and supported more efficient information management. The expansion of digital systems influenced regulatory frameworks, intellectual property management, labor practices, and data governance. Institutions gradually incorporated digital strategies into long-term planning and operational structures. Labor markets experienced significant changes due to technological advancement. Automation replaced some manual tasks while creating demand for technical, analytical, and managerial skills. Workforce training expanded in engineering, computer science, and information technology. Global supply chains shifted employment patterns across regions, contributing to industrial expansion in East Asia and restructuring in traditional manufacturing centers. Digital technologies influence professional work by increasing reliance on software tools, data systems, and communication networks. These developments reshaped labor distribution and skill requirements in multiple sectors. The social implications of the Third Industrial Revolution were substantial. Personal computing, mobile communication, and the Internet altered daily interactions, information access, and cultural distribution. Digital media expanded access to news, entertainment, and educational resources. Communication shifted from physical to digital channels, influencing personal relationships and organizational communication. Although the full impact of digital social structures emerged more prominently after 2005, the foundations were established during the concluding years of the revolution. Environmental considerations also emerged as digital technologies expanded. Semiconductor fabrication requires advanced materials and precise manufacturing conditions. Increased global trade raised concerns about energy consumption and emissions. Electronic waste became a growing issue due to rapid device turnover. At the same time, automation and digital management improved energy efficiency in manufacturing and transportation. Renewable energy research initiated during earlier energy crises continued to develop, supported by digital monitoring and control systems. The environmental implications of digital transformation became increasingly important in subsequent decades. The Third Industrial Revolution demonstrated the importance of foundational technologies enabling long-term transformation. Integrated circuits, packet switching networks, personal computing, industrial automation, and broadband communication established frameworks supporting continuous innovation. These systems operated interactively. Semiconductor advances enabled computing improvements. Computing supported automation. Automation required digital networks. Networks facilitated global coordination. Global production expanded semiconductor demand. This interdependence created a reinforcing technological cycle that sustained progress across sectors. By 2005, the global technological environment reflected the cumulative developments of the previous 5 decades. Broadband networks connected millions of households. Mobile communication devices supported widespread interpersonal communication. Personal computers were common in homes, schools, and workplaces. Automated logistics supported global supply chains. Digital finance enabled rapid international transactions. Industrial systems relied on robotics, CNC machinery, and digital control. Governments, corporations, and individuals operated within digital environments shaped by decades of technological progress. The legacy of the Third Industrial Revolution extends beyond specific devices or systems. It represents a structural transformation in how societies process information, produce goods, distribute resources, and communicate across distances. It altered institutional frameworks, economic patterns, and daily life. The infrastructure built during this period formed the basis for subsequent technological developments, including high-speed mobile networks, advanced artificial intelligence systems, cloud computing, and large-scale digital platforms. These later developments are rooted in the semiconductor, networking, and automation foundations established between 1958 and 2005. The Third Industrial Revolution, therefore, occupies a central position in modern global history. It reshaped the structure of economic activity, influenced geopolitical relationships, and established digital technologies as essential components of industrial systems. The transition from analog, electromechanical processes to digital, software-driven systems defined the technological character of the late 20th century and early 21st century. The revolution's legacy continues to shape global development and remains fundamental to understanding the evolution of contemporary technological and economic systems.